are up to 58, 59 people. I think we can probably start. And of course, this first period is set aside for helping people with homework questions, going over what people found, some show and tell if anyone has anything they want to show us. Does anyone have anything that they want to show or want to ask?
There was at least one person asking on Slack about the how to count the fringes on the Nevada Sentinel-1 interferogram. So I think they actually processed it correctly.
Yep.
They were getting confused by the fringes that were wrapping around and starting back down on the other side of the phase hill there. So they had a wrong count because they didn't notice that the fringes were starting to go the other way.
I'm wondering how the zero displacement contour is determined. Well, I mean, at some level, it's an arbitrary choice because all of the measurements of displacement we make within are relative, and we don't have an absolute frame of reference. It is possible if you have GPS data or continuous GPS stations that within your scene that you know the absolute position of, that you could potentially combine INSAR with GPS or GNSS data and actually figure out where zero displacement is. But for the exercise that we showed you there, we chose arbitrarily something in the far field that looked far enough away from the earthquake to not have moved in the earthquake. But that doesn't mean that your profile interpretation isn't valid. It just means that you would you could imagine that you add a static shift to the whole thing, up or down, based on any difference between zero on your profile and the true zero motion that you could measure with some other geodetic method.
But it's bringing up a really good point. It's important to understand that INSAR is a differential measurement and only shows you changes in space and time, and it doesn't provide you with an absolute measurement intrinsically. And when you present deformation maps, it's very important that you always also show what your reference is. So showing your reference location, the point of the area that you decided to use as your 0 point or your reference point, to show that always is also very important, so that it's clear what your deformations are measured against. Eric, can you look at the second question in chat about the ASF Python script? I'm assuming, is that a download Python script?
Yeah, I don't know what they mean exactly.
Well, when you use Vertex, you can choose to export your shopping cart as a Python script.
As a Python script, okay.
And if people are having problems,
I haven't used that option, so I don't know how it works.
Well, it's a script. So long as your credentials are fine, then you can use it. And it's sometimes helpful because if you've gone to the trouble of finding exactly the data you want in Vertex, then you can just download the Python script, upload it to OSL, and then download those frames.
Yeah, so I don't think it matters specifically where on OSL you upload this to, which folder, as long as you know where you put your data. But you should be able to run that on command line in a terminal on OSL, and in a folder of your choosing.
Yeah. Do you want to show how you upload a file in OSL? I think that's the actual question. Well, part of the actual question. So how do you actually go about uploading something? Silence. Well, I can show you. ASF friends are busy.
Oops. Yep.
Yeah. Okay. So you could be in your TopSap directory. You could make a new folder, you know, new data or something. You could go into that directory and you can upload a file. I don't have any download script here, but you know, you can upload something. I have a TopSap file. How about that? And then it's uploaded, and then you just execute the script that the download script. If you have one, by opening a terminal. Let's see. You want to. No, I'm getting lost. Where's my launcher? You can open a terminal, and then you can navigate to wherever you copied your thing. Geosync, UNAV code 22. It's in 2.2, and new data. You know, if you have a download script here, you could execute it using Python.
Maybe also show how to copy the notebook and make another copy in this directory.
Yeah, sure. Here is
right click on the file.
copy. Right click, paste. Then you can open it and start to change your things.
Right, so here you need to change this directory.
Yeah, there's a question that Paul put in from Slack, I guess. Folks ask.
Actually, this notebook is set up to start at the very top here. It sets the tutorial home directory to get CWD. That's the current working directory. So now that we made a copy of the notebook in this other directory, it's going to the processing will be done in this new directory and below it. So that's, I think that answers the question. Yeah, at least in this particular notebook, it uses that get CWD, and then it creates subdirectories beneath it. And
you could open your TopSap XML and your reference and secondary XML. Actually, here, look, yeah, here I have everything in one file. This is something I was processing overnight. But yeah, you would want to swap out in the reference part and in the secondary part the names of the SLC files that you want to use.
Yeah, I think people were doing that, and then they discovered that when they reran the cells that configure these files, they were overwritten because those are hard coded.
Yeah, well, you just don't run them.
Right. So I think one way, what I was thinking we might tell people is that in that configure inputs, you can go in and reach it and just change the hard coded names here.
You can, yeah. You could just put the names of your SLCs.
That way you don't have to do something outside of the notebook necessarily.
Yeah, that's a good point. There's the reference file, and here is the secondary file.
Yeah, but there's no instructions to do that necessarily, so I can imagine why people got a little confused.
Yeah.
Yeah, that's right. So the configuration file is auto-written, and this cell would need to be edited. That's correct.
Yeah, I think a way to solve that in the future would be to have another cell that basically says, defines the reference and secondary file names, and then change configure inputs to have those as input parameters, and then it would perhaps get written properly. But there's other stuff in here like range.
Yeah, the region of interest is hard coded for that specific area in Nevada.
Exactly, and the swath that's selected, all that stuff, I think needs to be clarified as to what's needed and what isn't needed.
Yeah, so you would want to change the swaths. You would want to comment out the region of interest, or change it to comment out something in XML. You put exclamation point and 2 dashes at the start and 2 dashes at the end, and then that would kind of just disappear from being executed.
Right.
Like these actually down here. Yeah, good point. Anything else that you would need to change? Let's have a look.
If you don't specify the region of interest, it basically figures it out from the bursts or the swath that those files specify. Is that correct?
Yeah, it tries to process the whole area of the reference slice.
Process the whole area of overlap, right, between the two. Sorry.
Yeah, the overlap between the two slices, yeah.
So if you tell it swath 3 and your region of interest is only in swath 1 and 2, you'll get a blank. You'll get a 0 result.
Yeah, and
Yes.
people have already discovered that yesterday, I think.
Okay. Yeah, I think that covers what we were debating this morning. I think we answered the questions correctly.
Yeah, let's see. I actually did. I did get some data yesterday from Vertex, so if I can remember where I put it, not a given. Yeah, okay. Nope, not there. Locations. This. Not that. Staging. Yeah. Okay. So here is a download script. Right, so you could look at it, what it does. It's a really long Python script, but it contains in it things like the URLs to the files, which you can try using instead if you have problems with running the script, as long as your credentials work. But basically, you just have to run it with Python like this. Type in your ASF password and sit back and wait. And there's a problem downloading. Why? France, what's going on?
I'm sure it's a user error.
It's really not wanting to work today. Well, okay, we can try something else. wget and all that. Internal server error. That doesn't sound like my fault.
Did you get those just now from Vertex, these links?
I got them last night.
Okay, I'm gonna ask if there's a data pool issue. Let's see.
Try curl. Another option, right? Yeah. Not happening today. What if I always, when you get a download problem like this, you can try executing the thing. It looks like you're down, France. That's not good for a training day.
I'm pinging the team.
But I did exactly what I just showed you yesterday on my own machine, and everything downloaded to the directory I was in using that script.
Are these Sentinel data? Are these?
Yep.
Okay.
Sentinel.
So I just got a message that apparently NASA Sentinel-1 distribution is down. I'll find out more.
Okay. In the meantime,
So our ingest and archive team is apparently aware and they're working on it.
all right, questions in my absence. Have people been answering these?
So conceptually, what Gareth did is right, but it seems like NASA has an access issue right now that we are working on.
So there's a load of questions. Did anyone answer them? I guess not. Could you go over how to interpret the INSAR data to determine the movement of each side of the fault?
From the Nevada earthquake.
I think that's from the Dinar earthquake. Notebook 2.1 is,
2.1 is, yeah, the Dinar earthquake.
yeah. Well, open that up again. Share. Where was I? I was here. All right, 2.1. Interpreting INSAR data. Try and make it. Everyone see this?
Yes, we can. Gareth, just I think your volume is a bit low. Is that just me compared to like Eric and other folks?
Or because I'm looking away from my microphone. Let me see. Put it more in harm's way. Okay, so here's the interferogram. Here is our arbitrary zero level mentioned earlier. You know, you choose somewhere away from the fault, away from the signal as your zero. And the important information about how you determine the direction of motion is contained in the figure caption in this case, because without being told what the sign convention is for deformation, you're not going to know a priori. You might have a convention that you use, but other people might not use it. So in this case, I was very clear or very careful to put in here that a cycle of colors from blue to yellow to red indicates an increase in distance between the satellite and the ground of 2.8 centimeters. But the point is that it's an increase in distance, which we call also positive range change. So assuming that all the motion that we're recording in this interferogram is vertical, then a positive range change indicates subsidence of the surface. So as you move from the outer fringes inwards, you see each cycle on the southwest side of the fault, which is the black line here, and that's the fault. Each cycle of fringes from blue to yellow to red is an increase in distance away from the satellite of 2.8 centimeters. So you can see 1, 2, 3, 4, 5, 6, 7, 8. There's about 20, 21 fringes, depending on the day and how good your eyesight is. It's hard to count sometimes in the really sort of high gradient area. But that means that as you move along this profile line up to the fault, actually up to about here, your subsidence is increasing. And actually, if you look here, you can see that these fringes start to wrap around potentially, which suggests that this is kind of the maximum displacement that you get on this side of the fault. And if it were coherent all the way up to the fault, maybe you can see some of these fringes continuous through here. Then they would probably wrap back around. And why you can't see anything here is actually the fringe gradient's really large, and maybe that's partly why it's decorrelated.
Plus the ground surface may have been disrupted by very the fault shaking.
That's true. And also there are lakes up against the ridge. This big area of decorrelation here is a lake, which is what you would probably expect to form at the foot of a ridge where the other side of the fault is going down in every earthquake. You create a little space for water to fill in a gap. So all of those things could cause you to lose your signal. On the other side of the fault, if you look at if you count from outer fringes inwards, what you see is instead of going from blue to yellow to red, you go from red to yellow to blue, red, yellow, blue, which means that the sense of motion of the ground on that side is in the opposite direction. Whereas this side was subsiding, the fringes here are consistent with range decrease, which we could interpret as a vertical uplift of the ground. And that's how that works. But it starts from having to know what the convention is for for your interferogram. If you process your interferometric pairs with the first date as the reference image, then you should, out of ICE, get an interferogram in range change, like this one, where a positive gradient equals an increase in distance from the satellite to the ground. But other people and other systems use a different sign convention. For example, we're going to talk about ARIA interferograms today. Sim will be on to talk about those. And ARIA uses the opposite sign convention to this for reasons that I don't know, but I'm sure they had their reasons. But that's the case. That unless you know what the sign convention is, you might not. You have to be careful in your interpretation.
It's something that there's a large variation of different. There's only two choices, so you have to figure out which one of the two somebody's used in their processing, or what you've done in your own processing. If you set the reference scene to be after the earthquake and the secondary before the earthquake, then you get the opposite sign convention, which is what the ARIA processing does for their interferograms. So
Alex Morland asks, is there a simple way to export the final geocoded unwrapped product? Yes, we have in the GDAL notebooks, there are examples of GDAL translate, which is a command you can run on the command line, or you can put in a notebook cell that will do it. You can also natively read ICE interferograms in QGIS. It's a supported format, so you can just open it in there and it should open properly. And if that's the software you use, then that's a pretty neat solution as well.
But you have to remember that the .unw.geo file is still in radians, so you need to convert that to meters by dividing by 4 pi and multiplying by the radar wavelength. True.
And you also need to remember to copy all the metadata files as well, not just the unwrapped.geo file, but the VRT file and the XML file. Typically, you should copy all of those. I have one question. Since TopSap doesn't use my local server, should I install GDAL on my local Jupyter? If GDAL doesn't open on your in OSL, you're probably using the wrong kernel.
Yeah, you may have not run in the UNAVCO kernel. Gareth, do you have your OpenSAR up? Can you point out where the kernel is identified? GDAL is installed in the UNAVCO kernel. You should not have to install it separately.
It's here.
Unless they're asking about their own local computer instead of the OSL
No,
server.
I think it's both. Because if you run the notebook with the wrong kernel, so you can have like this will be the default kernel or Python 3, but we want you to use UNAVCO. If you try and run it with a wrong kernel, you'll get that message, and you don't need to install GDAL on your home computer to get it to work in OSL. You only need to install GDAL on your home computer if you want to run these notebooks on your home computer.
But yeah, so and also on Jupyter Hub, just if you are in the UNAVCO kernel, this code cell should run fine. You wouldn't have to install GDAL separately because it should be already installed. Can you rerun and make sure that you have the kernel set and see if that fixes it? Fatia? Yeah, okay, excellent. Perfect. Thank you, Fatia, for the feedback.
Anyone save the chat from yesterday? Yes, they're all uploaded. And they get uploaded. So now I've just flipped to the syllabus. I think I even put the link here. Right, they're not all here yet, but Melissa has access to these, and presumably Becca as well. We can make sure they're put in here. We made a folder to put them in. So we can try and find them and make sure they're uploaded there.
Yeah, they should either be in Melissa's inbox or Becca's inbox.
Could you show how to do ionosphere correction using TopSap? That might be a bit of a lengthy diversion.
We are going to discuss how to run the ionosphere corrections in StripMap app. It's a little bit more complicated with TopSap, so it's kind of an advanced topic. I certainly can't do it in the next half hour.
Is there a notebook though that we could
There's
share?
a notebook, yes, for the ionosphere corrections with StripMap app.
Okay.
Yeah, we do that. When is it? Today or
That's
tomorrow?
tomorrow.
Tomorrow, yeah. There's a whole module on toposphere and ionosphere corrections, and basically what we're going to do is use the strip map interferogram processing we did on Monday, that hopefully you finished for homework, and remove the ionosphere contribution to that interferogram. If you remember, if you looked at it, there were lots of fringes across that interferogram, and you can get rid of them using this module. And hopefully once you've been through the process in StripMap app, it's not such a huge stretch to imagine how it works in TopSap.
Yeah, it works basically the same. It's doing the same kind of split spectrum estimate of ionosphere. And we'll be doing that for NISAR for sure. That's part of dealing with L-band data, and because of the especially the Sentinel-1 has some ionospheric effects that usually don't have a big effect, but sometimes they're noticeable. Because of this, because of the top scanning during each burst, in the burst overlap, where there's two bursts that overlap and they have a different along track look direction, because the ionosphere actually causes some along track shift in the radar image, you can actually start to see phase discontinuities at the burst boundaries that's caused by the ionosphere. And that's one of the things that the TopSap ionosphere correction fixes, but it's kind of a long explanation. We have a paper written on that, the Liang et al. I think it's in the notebook at the end. It's kind of an advanced topic.
Okay, if we don't know the swaths of our area of interest, how can we set the parameter swaths? Well, it really depends what you're trying to do, but one thing to be aware of is that if you know the sense of motion of your satellite, whether it's ascending or descending, you can basically eyeball your area of interest in terms of whether it's in the near range, which means the side that's closest to the satellite, or the far range, that's the side that's furthest away. Then if you mentally divide the frame into into thirds, then the third that's closest to the near range is subswath 1. The middle subswath is subswath 2, and the far range is subswath 3. So looking at something like the vertex search tool, we can do that.
The other option is just to not specify the swath, and then it'll use all 3 subswaths.
That's true.
And if you specify the area of interest, it'll determine which subswaths it needs to use. We did both in the notebook, but it's not necessary to do both.
Yeah, so the key is it's an optional parameter to set if you want to be specific about the swath you want to process.
We wanted to have the notebook processing just a small area so that it would run quickly. Otherwise, it would have taken 3 times as long to do 3 subswaths.
questions.
All great questions. Do you have more?
I have a question about the interferogram process. I wonder if I could share my screen.
Yes, please.
So, can you see my screen?
Yep.
So I processed an interferogram, or the area of interest I cared about was on the border of two different scenes. So I processed two different scenes, and they're not exactly lining up. And I think that's because one of these I didn't process with ESD. But I'm wondering what you guys think, if that would cause this kind of mismatch in the fringes.
So when you processed it, you processed the two frames separately.
Yes.
There is a way, just FYI, of like combining two consecutive frames into a single processing. That would help probably.
How do you would you start before you even import it into ICE, or do you give ICE both of the scenes?
That happens at the XML file level.
Okay.
When you have two slices of Sentinel-1 data, then you can, instead of just specifying one scene on in the reference.xml file, you can specify two scenes inside a list. So you put square brackets,
Right.
scene 1, comma, scene 2, close square bracket.
Okay.
And then it'll automatically go through and figure out which bursts to pull from which Sentinel-1 scene.
Okay. And so the thing you just talked about, so like give it all the bursts and then just give it a region of interest and it'll figure out the rest.
Yes, it'll figure out which bursts it needs to pull from which scene.
Cool. Thank you. Appreciate it.
Yeah. So instead of like a single file name, you would have a square bracket
Right.
and
then separate.
and then a list.
I think you don't put the quotes. It used to be that you had to put the quotes, but I think now you don't.
Anyway, if you do,
Okay.
it still works.
Cool.
And just
Yeah.
FYI, so the ICE team is actually working right now in an access project to sort of update the code to fully leverage bursts. So if you have an AOI, right now it would pull, both frames, and you'd have to process the full frames. And so in the future, there will be in the very near future capability to do burst-based processing and limit yourself to only the bursts you actually need.
Cool.
And then this issue should go away also.
But and the other thing is there probably is significant north-south deformation in that area. And so if it is a burst boundary, you might still see a discontinuity in the fringes due to the change in line of sight as you cross the burst boundary. Because of the tops mode, it sweeps forwards and backwards. So
I
the
see.
northernmost
Okay.
part of like one burst is going to have a northward pointing incidence, and then line of sight angle, and then the southmost
Right.
part of the burst to the north would pointing the other way. So sometimes you get discontinuities like this, which are real in that they reflect northward motion.
Right. Okay. Cool. Can I ask one more question that I kind of asked Eric already in Slack, but I wanted to get some clarification?
Sure.
Sure.
I'm just trying to figure out satellite looking geometry in this image. So if I'm, where was it? So like I'm looking at a Sentinel-1 ascending node, which means I should be looking like in this direction, right? And traveling in this direction.
Yep.
So then from the code, if you look at the LOS RDR XML file or the geo file, it gives you an azimuth of 257. So that's just the direction this satellite is pointing or traveling?
Pointing. And just
Pointing,
the
okay.
reason that we just talked about, that because you used to be able to just use the heading direction of the satellite and like add 90 degrees to it, and because it was always pointing to the right.
Right.
But that's not the case anymore, because the beam is
Right.
sweeping backwards and forwards. To get the accurate line of sight information, you need to account for that. So now we use the pointing azimuth from the satellite to the target.
Right. And I guess because Eric was just saying too that some of them are going to be some of them look left already, and NICE is going to be looking left. So it makes more sense to just give an azimuth of the point. Gotcha. Sweet. Thank you. That makes a lot more sense.
And the angles are always negative for some reason.
Yeah.
So
Let's
negative
yeah.
250.
Well, and ICE uses a different convention for the angles than right pack used to use. So it's and Gamma uses yet another definition of mammal and the azimuth angle. So it's you have to be careful with do some sanity checking about where
Right.
you know it's ascending, it should be going north. Or if you know it's descending, it should be going south. There's a lot of different conventions. Sometimes it's measured from north, sometimes it's measured from east with the math convention for angles.
Right.
Unfortunately, there's different softwares use different conventions.
Gotcha. Okay. Thank you guys so much.
We're going to cover this a bit in the next session as well.
Okay. Thanks.
Who else has a question?
There was also a question of how can we define if there's atmospheric errors in our interferogram? That's a big topic.
That's also going to be discussed. Are we still talking about that in tomorrow?
Yeah, I'm going to be talking about that tomorrow in the troposphere and ionosphere session. So I think maybe we can defer that to tomorrow.
Yeah, and if you have particular interferograms that you're curious about, you can show us, and we can give you our expert judgment.
We have what, another 10 minutes?
Normally speaking, if you have an interferogram in which you know there's no big earthquakes or other sources of large sudden movement, and you see lots of fringes, there's a good chance that they're atmospheric. All right, you can show one. Cool. It's better than just talking about it.
Always love to see fringes. Please show.
Even if they're atmosphere.
Even if they're atmosphere.
Another thing that you often see with atmosphere is that because the delay of the signal, the radar getting to the ground is related to how much air the radar goes through, and there's less air, there's less atmosphere above a high mountain than there is above a kind of low valley. Sometimes the fringes look like the topography. That's another giveaway.
Yes, well, I'll be talking about that tomorrow. Also, there's topographically correlated atmosphere due to water vapor variations in the lower part of the troposphere.
Yeah, can I share my screen?
Yes, please.
Yes.
Aha. Okay.
So these interferograms were created during my master diploma.
Okay.
Uh-huh.
So this is over oil field in Kazakhstan.
Okay.
Okay.
I can believe it. Some
Yeah,
areas of
it's Sentinel
injection,
data.
some areas where you're injecting and some extracting, maybe. I see dots. That could be
Very cool interferogram.
yeah. But
Yeah,
okay.
unfortunately, I didn't have data from GPS.
You don't necessarily need it. I think you can see a lot of detail in here.
So what's your question specifically?
So these are two different interferograms of different dates?
Yeah.
Yes, I wasn't sure for this part if there is, I mean, subsidence or uplift.
So could you show us the dates? I think that's important too, to know if they have any dates in common. So they have a different start date.
Oh, there's one date in common. Okay.
Yeah.
Yes, so they have the same start date, but two different end dates.
Yep.
So
Yeah.
that means that the atmosphere that was in that start date is going to be in both of the interferograms, but the atmosphere that was in of the end date is going to be or the reference scene is different. So then the part of the atmosphere, what we see is the difference between the atmosphere of the two dates. So if one date is the same, then half of the atmosphere is the same, but half of the atmosphere is different. So it's but the fact that these two interferograms both show almost exactly the same signal is a a pretty good indication that it's almost surely actual ground displacements rather than atmosphere. You can see that there are some features that are different between the two interferograms.
Mhm.
You can see in the left one that there are these stripes in the northwest, and that could be an atmospheric standing wave.
Yes.
See it.
But it's interesting that, for example, if you see for another days, some of them just disappeared, like here.
Yes. Okay. So you have a number of interferograms here. Okay, so that's great.
Yeah.
Some of them may have, do they have shorter timeline?
Also, yeah, I mean, if the deformation is correlated with time or time dependent.
Yeah, it's increasing with time.
Because, you know, I see these are short time span interferograms. They have a smaller signal that tracks. You know, if it's a fluid extraction signal, then of course the longer the time span you have, the more subsidence you should have for that process.
I think there's a, you know, as we go on with the course, the stuff you will hear tomorrow and on Friday is going to be really important for this, because you have a series of interferograms here. So on Friday, Yunjun is going to talk to you about how you can take all of these to invert them to a full deformation time series. And that step is actually also going to help you suppress some more of the atmospheric noise and actually tease out, you know, what's deformation and how deformation changes with time. So that's going to be nice to look at on Friday. And tomorrow, Eric is going to talk to you a little bit about what atmospheric delay looks like and what types of atmospheric delay we have and what sort of their spatial expressions are. So hopefully,
Thank you.
What you'll hear about tomorrow and on Friday is going to help you process these data sets further.
Yeah, and you can see more features here. I mean, for example, in the northeast corner, there's a sort of a step up in phase, which is probably related to topography. I can see that there's a kind of a flat area in the underlying image, which correlates with that. So that could be atmospheric. That could be a static atmosphere signal. And in the southwest corner, where all those red signals are, again, I think that's probably atmosphere that was present on the date that these.
Yeah, in fact, some of that red signal in the southwest corner may actually be the new phase closure effect that we've only started to realize is in a lot of interferograms just in the last year or two, with that Yu-Ji Chen's paper that was just published, or maybe, yeah, I think it's actually published. It's at least been submitted. I don't remember if it came out yet, but there's some certain types of surfaces. This looks like it's a salt flat surface, and depending on how you form your interferograms, you can get some interesting phase signals that are due to the way the radar is interacting with the surface. It can be depending on how long your time interval is. So it's that's another thing to be careful with. We don't really cover that in this course because it's actually a very new feature phenomenology that we haven't really completely understood yet.
Yunjun has a notebook.
Yunjun, it's been added to MintPy, so Yunjun's going to mention it.
But I think we decided it was too complicated to
It's very, very complicated to understand. We're just starting to understand ourselves.
Now you're just raising questions for.
Yes, you're just throwing like monkey wrenches.
So what is phase closure? In the simplest sense, if you make 3 interferograms from 3 dates, you could imagine this is.
If you have 3 dates, you have A, B, and C. You make an interferogram AB, an interferogram BC, and you make an interferogram AC. And if you add A, B, and BC, you get a different answer than the AC interferogram. And that's normally if the phase was what we expected, the difference would be 0. But if it's non-zero, then we have a phase closure error, and it's due to these weird phenomena that we are still trying to understand.
That may be related to soil moisture.
Okay, thanks for your opinions.
Yeah, so this is this. I wouldn't at this stage worry too much about phase closure right now, but so what you're showing here, this is actually a really nice example, and I think once you know more about how to use MinPy and time series analysis, I think you'll get some really nice results for this side.
Okay,
So
thank
look
you.
forward to tomorrow and Friday.
Okay.
Thanks for showing your examples.
Right,
Yeah, welcome.
We've made it to 10:50, and in our schedule we have a break here. So maybe we should take a break until 11. So go off and have a short walk, come back refreshed.
Yeah, should we
Talking
show a
about,
break before Gareth starts? Yep.
see you in a bit.
Awesome. Thanks for all the good questions. So we take a 5-minute break, 7-minute break.
Right then. Everyone's back, maybe. I can grab back the control of the screen. Okay, so the next exercise is going to be 3.1, module 3.1 on preparing data for modeling. And really, this is not just about preparing data for modeling, but also about modeling as well. So I will share my screen. Hopefully you can see it. I can mess around a little bit to get the chat live so I can see it. Okay, so what we're going to do is going to go to GeoSync, UNAVCO 2022, and the Preparing INSAR Data for Modeling notebooks. And we're going to look first at this notebook called Arcada LOS Components. And hopefully you can see this. Okay, so this notebook is designed to show you how surface deformation resolves into interferograms. Because if we are going to start thinking about how we can come up with physical models to represent surface deformation processes, we want to understand how those models actually look if you project them into the radar line of sight. This kind of insight is very useful if you're trying to understand what you're seeing. And unlike the very simple models we did on Monday with the MOGI source, which are radially symmetric and pretty simple to understand and to identify, when you're actually dealing with movement on a rectangular surface, whether it be shear movement, which you would get in earthquakes, or opening movement, which you would get in dike intrusions or sill intrusions, those are very much more complicated than the sorts of things you see with a MOGI model. So we're going to talk about one class of dislocation model. There's models that involve rectangular surfaces, and this is called the Arcada model, which is probably the most common model used to model earthquakes. So hopefully these things work. They did last week when I tested them. But to start off with, in the notebook we're running, we have to import a load of dependencies. So as long as you have the UNAVCO kernel operating, this should work. And what we're loading is the Arcada code, some math functions. NumPy allows us to deal with arrays of numbers. There's some math functions, some plotting functions, and some other stuff. So the Arcada model. So here's a figure actually from Arcada's webpage that describes what we are trying to, the things that we have to specify in order to model slip on a fault, or indeed a dike opening. We have to define a rectangular surface underground. We have to define its orientation. We have to define, which we call its strike, so the angle that it makes with north. We have to define its dip, which is its angle of inclination, whether it's vertical or horizontal or some angle in between. It's defined by the angle it makes with the horizontal, which we call the dip. We have to have a reference point within the fault, which we use to locate it with respect to observation points, and we have to know also its movement, both in the along strike direction, so the direction that it's oriented, and also in the down dip direction, the direction that it's tilted. So if we define all those things, we can calculate a theoretical deformation field that goes with it. To translate it into real coordinates is a bit of a a hassle. I wouldn't want, having figured out how to do it, I wouldn't necessarily try and make you do it yourselves. But there's a lot of geometry and trigonometry involved in trying to actually locate this thing in space, and I have done all that, and most of this notebook is just going through all these geometrical things that you have to do in order to get it to work. There are a couple more things that we have to set. We have to set the elastic parameters for the crust. There normally we define two elastic moduli, lambda and mu. These are the Lame elastic parameters for those of you who know about seismology and elastic waves. For those of you who don't, it doesn't really matter for the purposes of this exercise, but we typically use something like 30 gigapascals for both of them, and that will give you a reasonable reasonable starting point. And the other thing we want to specify is the geometry of our fault. We want to give it some parameters that describe the orientation of the fault. So we're giving it a strike angle of 1, which means the fault is basically pointing towards 1 degrees, which is more or less north, if north was 0. The dip of 85 degrees, that's very steep, and the dip would be close to vertical and dipping slightly to the east. A rake of -1, that makes this a left lateral fault. A slip of 2 meters, and some other features of the fault. So its dimensions, its length, 15 kilometers, 15,000 meters. Its width, the extent it has underground, 10,000 meters, so 10 kilometers, and the center of that fault is at 6,000 meters depth. So that means that the fault extends from 1 kilometer below ground to 11 kilometers below ground, more or less. We also define its the center. If you project that center of the fault to the surface, we're going to say that's at 0, 0 on our coordinate system. So right in the middle of our coordinate system. Okay, so you can run these cells. Oh, I have to run that one as well. The rest that we're doing here is geometry. I'm not going to dwell on it because we don't have much time. But there's a load of things we have to do to relate our preferred fault geometry to the points around it. If anyone has any questions about this later, I can go into it in more detail. But for now, let's just say we have set up everything so that it will produce the deformation in the coordinate system that we want, which is, as you see here, a grid that is 50 kilometers wide. It goes from minus 25,000 meters to plus 25,000 meters in both X and Y. And we're having 101 pixels in both directions, which means each grid pixel is 500 meters. That's right. We're going to make a bunch of arrays to put the results in, and we run through 2 loops to calculate the deformation at every pixel in all 3 displacement directions. So east-west, which would be the X coordinate, north-south, which would be the Y coordinate, and up-down, which would be the Z coordinate. And if you run this cell, it basically runs the Okada code and calculates those displacements. And then at the bottom, it plots them. So hopefully I can I make this bigger? I would like to extend this cell. Well, it's differently on different machines, I guess. But if you look here, what we're plotting are 3 sets of displacements: the displacements in the east direction, the displacements in the north direction, and the displacements in the Z direction.
If you right-click it, Gareth, and then go to disable scrolling for outputs.
That would be awesome. Thank you.
Welcome.
So if we run this, what we see is the displacements, and they go up to about 50 centimeters in each direction for this theoretical fault. Now this is what we call a north-south strike slip fault, which means the direction of slip is in the direction of strike. Strike is north-south. And so, unsurprisingly, perhaps the maximum displacement we see is in the north-south direction in this Y displacement plot. We get about 50 centimeters of movement of one side of the fault northwards and the other side of the fault southwards. This would be what we call a left lateral pattern of slip, in that if you're standing on one side of the fault and looking across it, the other side of the fault moves to the left. So this side is moving south and this side is moving north, and that gives you left lateral displacement. If you look at some of these other things, you see some interesting features. You see that there is east-west displacement, even though this is a north-south fault moving north and south. And that's because the fault ends, it's finite in length. And so there is sort of distortion and warping of the elastic material, basically the crust of the Earth, around those ends. So you get this this movement to the east in the north and to the west in the south, which is just accommodating that finite fault and the warping of the crust at the ends. And you also see that you get some vertical displacements at the ends of the fault. So depending where you are, it either goes up or down. It goes up here because the fault is moving and squeezing this area here and causing it to warp upwards. And similarly, this area with fault is moving, the fault is moving to the north here. It's stretching this area and causing it to warp downwards. So all these additional effects are present in the elastic deformation associated with the movement of a fault. It's not just the movement in the direction of the fault. And that strongly affects how we see this displacement signal in INSAR. So what we've got then is three components of displacement, but we want to know how this appears in an interferogram. As we were just discussing before the break, you can output from ICE a series of two angles for every pixel that tell you the pointing direction of the satellite, and also the incidence of the angle of the satellite radar and the ground. So if you know those two things, you can calculate a vector that points in the direction of the satellite pointing. And those angles are represented here as phi and theta. Phi for an azimuth, the pointing direction, and theta for the incidence with the ground. And I'm not going to go through the math here. I think I go through it somewhat tomorrow, or at least the idea of it. But anyway, if you want to calculate the three components of pointing in terms of the X contribution, so the east contribution to pointing, the Y contribution to pointing, and the Z contribution to pointing, and you know these two angles for the pixel that you're interested in, then basically if you evaluate these three terms of the vector, you will get your three-dimensional pointing vector. So here I have specified two representative values of theta and phi. 39 degrees for incidence is approximately the incidence angle of the center of the Sentinel-1 swath, and minus 260, if you use that, is consistent with an ascending track viewing geometry. So if your interferogram is an ascending track interferogram, you would use an angle of minus 260 approximately to give you the right pointing direction. And if it were descending, you would use about minus 100, which, if you want to switch between these, you just have to uncomment one and comment out the other. I will start though with an ascending interferogram. Okay, so you evaluate those three components, and we print them out here. You can see that the three components of the interferogram or of the line of sight. There's an X component, which is 0.619 or 0.62. There's a vertical component, which is negative 0.77. And there's a north component, which is 0.1. So from the relative sizes of these, you can tell that, that the east and the north, the east and the vertical components are the most important, and the north is quite a bit smaller. And that is because the satellite is in a polar orbit. If we're imagining Sentinel-1, it flies from south to north. And it does so in a way that it synchronizes with the sun, so that it can collect energy from its solar panels as it's orbiting the Earth. So in that sense, it's in an orbit which goes always north to south or south to north, and the radar points to the right, which means that the contributions from the east displacement and the north displacement are largest. So we are most sensitive to the north component, the vertical component. I keep saying north. Most sensitive to vertical. You can see the sign of the vertical component is negative, and that's because the satellite is pointing down towards the ground. And in this case, we have a positive east component, so the satellite is also pointing to the east and very slightly to the north. So that's the pointing vector. And then all we have to do in order to represent what the INSAR is going to see when this displacement field is resolved into line of sight is to take the dot product between the displacement at a pixel in terms of these three components with the pointing vector that we've just calculated here. So it's a dot product. It's pretty straightforward to do. And so, yeah, we just multiply each one by its pointing vector component and add them up and plot them. And what you get is how these three components of displacement map into line of sight. So you see, really, the point is to compare what you get here with what we had before. So you see that the X component contributes a moderate amount of signal. The Y component contributes almost nothing. So even though the Y component of displacement is the largest, when you calculate the displacement field for the earthquake, because the Y component of line of sight is so small in terms of the pointing vector, that very large displacement gets multiplied by a small number and basically contributes very little to the interferogram. On the other hand, even though the vertical component here is small compared to the north component, because INSAR is sensitive to it, it still contributes a good amount of signal to the interferogram. And then the interferogram is the sum of these three scaled components, which is what you get on the right here. And perhaps this looks quite unlike what you might expect to see. You have a lot of signal on one side of the fault, and almost no signal on the other side of the fault. It looks pretty weird and asymmetric, but it can be understood in terms of what you see here. So
It looks like the BAM earthquake.
That's a reason for that. Actually, the BAM earthquake was right lateral, so I should change the rate to 180. But yeah, what is happening is you can see that the east component and the north and the vertical component are adding and canceling on one side of the fault. So you add this signal here to this signal here, a positive signal to a negative signal, and you get much less signal when you add those two things together. You add a negative signal to a positive signal, and again, they kind of cancel out. And on the other side here, you have a positive signal added to a positive signal, so you get a bigger positive signal, and a negative signal adding to a negative signal, you get a bigger negative signal. And in the end, you see this kind of constructive interference on one side and destructive on the other, and you get this very asymmetric deformation pattern. The question is, what is the unit of X and Y axis in these plots? Everything is plotted in meters here. So the displacements are in meters on this color scale, and the coordinates are in meters as well. So Tamara asked, so according to this, we could know beforehand if a descending or an ascending flight would be better to use in a specific structure if we know the expected displacement. In some sense, yes. Usually it's good to use both anyway, because you still get constraints on the deformation from both. But if you wanted to prioritize one, then yes, you could use this kind of model would give you a good sense of which one you should try and use. And of course, with earthquakes anyway, we have seismic solutions to what kind of earthquake it was that are available within minutes to hours of the earthquake. So you could plan your work before the images are even collected. And in the past, of course, we would do this. We would actually request that space agencies collect certain data. Based on
Although the standard seismic moment tensor solution has two different solutions, the east-west fault and a north-south fault. So we don't always know which one it is before we see the interferogram.
That's true.
When we do see the interferogram, we know immediately.
That's right. So I have another notebook which does the same kind of thing, but rather than just doing one, it does both. That makes both the ascending and descending interferogram at the same time, using basically the same numbers I just showed you. So if you run through this one, the ascending descending notebook, it just produces this compendium of models that shows what happens. So this is the same deal, and this actually is the BAM earthquake model. It's a right lateral fault. That if you feed a north-south strike set fault into this, you'll get the following displacement fields, you'll get the following components of line of sight. And if I remember right, it's plotting, it plots ascending first and then descending. Okay, so this is the ascending expected interferogram, and this is the descending one. And you'll see for this particular example, the difference between the ascending and descending interferograms is that you flip the entire deformation field from one side of the fault to the other, and that's all because the primary thing that changes between the two interferograms is how the east component of displacement resolves into line of sight. You can see in this ascending interferogram, the north side of the deformation is negative, and in the descending it's positive, and vice versa. So you can see that reversing the east component reverses the whole interferogram, more or less. The interferogram is anti-symmetric. These two examples. So that's a fairly interesting. It was a fairly interesting thing for us. First time we saw this pattern, we didn't really understand why. We only saw deformation on one side of the fault. But if you run a model like this, then you can get it. Of course, you don't have to use the example I showed you. You can change these parameters. So you wonder, for example, what if instead of striking to the north, what if this fault was striking, say, to the east? Okay, so you can change the strike from 359 to something like 90 or 91 degrees. You can rerun this thing. And now what you see is that, of course, now the east component of displacement is large, the largest. You have some deformation at the ends of the fault, like we saw in the previous example. The north component has some movement in it, and you also get vertical. But now, of course, because INSAR is sensitive to the east component, the east component dominates the interferogram. And you can see that there is again an anti-symmetry between the two interferograms. You see that you get positive deformation on one side and negative on the other in the ascending interferogram. The pattern is reversed in the descending interferogram. So the north is negative and the south is positive. And that is again because you're reversing the line of the pointing direction from pointing to the east for the ascending interferogram, pointing to the west for the descending interferogram. And then there's a small contribution from the vertical motions at the ends of the fault, which are shown here, that change the kind of the orientation of the fringes a little, depending whether there's negative or positive displacement in the vertical. So this allows you to, you can input whatever parameters for the fault you want, and you can see what you would get as a result. And this is helpful because now we're going to actually try and make a model from some INSAR data. Are there any more questions about this whilst I have a sip of water? how to
There's a
calculate.
question about the units. I guess all the units here are meters, both the displacement units and the map horizontal units.
Yep. How to calculate residual and misfit using the observed displacement like the MOGI model. Well, we'll get into that actually. Not with the MOGI model. I will show you how we do it for Ricarda, and you can try and extrapolate to other types of model.
Yeah, so MOGI was just an example of a model that exists, a simple model for point sources. This is a different kind of geophysical process. So it requires slightly more complex modeling. And so Okada is one approach that you can use here.
Thanks. Yeah.
The Okada model has 5 parameters and the fault slip model has 10.
Right. Yeah, or 9. So we have a notebook called Quadri Decomposition. I mentioned, I think, on Monday that we almost never calculate the penalty function, the misfit, or run the model using all of the pixels. Although now I realize that we did actually do that in France's example. So we'll do that. We'll show you a way of like reducing the number of data points that you have to model, and that method is called a Quadri decomposition. The basic idea is you take data and you calculate the variance of that data, maybe for a sub area of your data, like a sub-region. And the variance of the data, if it's above a certain threshold, that indicates that there is something interesting going on in there. And so what we're going to do is divide that area into 4 and then repeat the exercise. So if there is a large variance in one area of your data, what happens is that you subdivide the areas more and more until like you have much smaller areas that have a constant variance. So it focuses the sampling of your interferogram to the places where there are features in your interferogram, basically. And areas that are far away that have very little signal do not get subdivided and so are represented as big rectangles. That's the idea. And luckily, someone has coded it up for us, so we don't have to figure out how to code it up yourself. I did do it actually as part of my PhD, and it's a bit of a gnarly code to write. It was a recursive function. I was very proud of that, but apart from that, it was very complicated and it took a while to figure out. And this works very well, and we don't have to do anything. It runs in Python, and we can run it in a notebook. So to start this run through, basically we can import these functions. Kite is the name of the routine that does the Quadri decomposition. And if you're not me and you haven't downloaded and you don't have the interferogram already in your file space, basically executing the second cell will download a bunch of files. And I think if I run it, it doesn't re-download them. Oh, I don't know if that's true actually. Maybe it is re-downloading them. Anyway, if you execute this cell, oh, it's going to re-download them. This imports an interferogram of an earthquake from Turkey that happened a couple of years ago. It's a strike slip earthquake, and we'll get all the interferogram files that we need to do this kind of modeling. So hopefully this runs and you can run this, and I see people are answering questions. Let me see.
Which data is this interferogram from?
It's Sentinel-1, and it's the Elazig earthquake on the East Anatolian Fault. Happened when I was on a train to Durham in January 2020, I think. I remember emailing people about it from the train. And yes, these are pre-processed interferograms. what we intend for you to do for homework is to model a different earthquake to this one. So if you have processed an earthquake as part of homework for an earlier exercise, you can use that. We're also planning, although we haven't quite done it yet, to stage more data for another earthquake that you can use if you don't want to process your own. But right now, we're going to download these files, and once they're done, you can execute this code cell, and it will list the sizes of your files, and you'll see it's done. But these files are pretty large, 230 megabytes each. It's a fairly big earthquake. And what we're going to do is we're going to load these files into Python and look at them. So here are some file names that you might want to use. Built top of phase unwrapped.geo, if we talked about yesterday. That is the name that's given to the final unwrapped geocoded interferogram. It's also filtered. We're going to load in the correlation file, top of phase.core.geo, and we're going to load in a water mask, which is an optional file that actually just shows you where the bodies of water are in this interferogram. And depending how you process and unwrap your interferogram, you may not need these. If you remember, we discussed yesterday, if you use the ISCE unwrapper, then it already masks out the incoherent areas, and so you won't need a water mask or a coherent correlation file. Basically, it's already masked for those things. So here we can specify a couple of things. We can specify the radar wavelength because Kite wants it and complains that that ICE doesn't have it in its metadata. I don't know if anyone plans to solve that, ICE3. And also a correlation threshold, which we're specifying quite a low threshold here. You could see what happens when you change that number. You could mask out more low correlation areas. So I'll run that. And the first thing to do is to import the interferogram into the Quadri code, which is called Kite. Did I forget to run this cell? Yes, I did. Don't forget to execute your cells, people. And this basically uses GDAL to load the interferogram into Kite. And Kite has now imported it, and we can plot it. When you run it, it makes a nice little plot of the interferogram. Okay, so what do we see here? We see negative displacement on one side of the fault. The fault presumably is somewhere through here. And positive displacement on the south side of the fault. Remember, of course, we're dealing with range change. So positive means movement away from the fault. Negative means moves towards the fault. This is an ascending interferogram, so it's flying from south to north and it's pointing to the east, which means that a positive displacement here means it's moving to the east, and a negative displacement here is moving to the west. This is also a left lateral strike slip fault. So if you wanted to model what that might look like, I guess you would go in here and make the rake like 1 or something like that, and run everything. And our ascending interferogram should have negative in the north and positive in the south, and it does, which is reassuring. The first time I processed this, I processed the images in the wrong order, and I thought for a minute I turned the East Anatolian fault right lateral, which was a surprise because we know that it's a left lateral fault. It's a plate boundary, the Anatolian plate. Anyway, here's our interferogram, but we want to mask some stuff out. So we're going to load in a couple more things. We're going to load in the correlation information, and we're going to load in the water mask. And when you load those in, that's hopefully it's happy. We're going to convert our displacements to meters by multiplying by lambda over 4 pi.
Gareth,
Yes.
there's a couple of questions. So one of them is, can you go back to what you just did to change the change you did in parameters just a second ago, please? That was
Sure.
very fast.
I just changed the rake to 1. Also, maybe change the strike to, I don't know, 60. Let's do that. A strike of 60 and a rake of 1. And run again. Whoa.
And there's a related question, is basically asks what kinds of phenomena that the Arcada model can be used for.
It can be used for earthquakes. It can be used for interseismic loading of faults. It can be used for post-seismic after slip and fault creep, all of which are basically shear movement on a rectangular surface. And then you can also use Arcada to do opening. So instead of shearing, you can specify the third component, which is opening. So that works for igneous intrusions and maybe other injections of fluids. I've seen people use it for geothermal reservoirs as well. So those sorts of things. It's a bit more versatile than a Mogi source. You can actually, if you make your rectangular source really small, you can get a very similar result to the Mogi model for opening.
And there's a question, can it be used for fracture detection?
I mean, detection depends what you mean by fractures. You mean fracture opening, volume change, potentially. I mean, there are probably other methods you would use. You can use it for poroelastic processes, which are basically dilation and contraction of pore spaces, by running 2 models with different elastic parameters, but the same slip on the fault. You can use it for that. Perhaps this is something we could discuss more in office hours, because I think if I spend a lot of time talking about this, we could go off topic really fast, and I've got a few things to get through. Is there any reference of how much time frame interferograms we need to look at creeping faults? I mean, I think for creeping faults, the best thing to do is time series INSAR, which is what we're going to talk about next, and for the sort of the second half of the course.
Yeah, Tamara, in the end, if you have a very small deformation like this, you would not only use a single interferogram, but a series of them, and Friday hopefully will elucidate that a little bit.
So what we're seeing here is a magnitude 6.7 earthquake, so it has large surface displacements compared to what you would get with creep. Okay, so we've converted our displacements into meters. This step here masks out water, which is everything in the water mask that is not equal to 1, basically, and also everything that is below our correlation threshold in our interferogram. So if you do that, then we can see what we've masked out. We've masked out some lakes and a few incoherent spots, but they're just spots. We can tell what the sense of motion of this fault is that we're looking at. I already told you it was right, a left lateral fault, just from which way each side of the fault is moving. But you can also see here, this is the Euphrates River, and it has a fairly substantial, like 15 to 20 kilometer offset across the East Anatolian fault from just the movement of that fault over time. And again, you can see the river steps to the left as you go across the fault, which shows you it's a left lateral fault. All right, so now to actually downsampling the interferogram, there's a routine just called Quadri. So I should back up and say this thing SC that we have generated is an object that contains the interferogram now converted to displacement, and we can tell it to quadri the data just by saying our quadri thing is equal to our scene quad.quadtree. And if you run that, it does the decomposition of your interferogram. Or it does all the prep for the decomposition of your interferogram, and it takes a little while to run. But then we can specify some parameters in a minute that control how it works. So these are generally trial and error numbers that we would use. For example, we specify the variance threshold in meters squared, and you have to try and by trial and error see what an appropriate threshold is. But by trial and error, I find 0.02 is a good number. You have to say how many nulls are allowed in a box. So if, for example, you have this river, you might want to allow a certain number of null values in an area so that it doesn't divide your data up around like areas where there's no data. You can also define how big and how small your maximum box sizes will be. I've set the maximum size to be 0.2 degrees of longitude or latitude, and the minimum box size to be 1/100th of a degree. Anyway, if you run this, it applies those parameters. You can see how many things it's divided your interferogram into, and it's divided them into 194 what Kite calls leaves. And you can look at them all if you want. It shows you their location and their average value. But I find the best way of looking at these is to plot them as boxes. So if you run this, you now get your downsampled interferogram. So what you can see is that there are some large areas that are far away from where the signal is, because there's not much variation in the signal out here. But as you get closer to where we think the fault is, then you'll see that the size of these boxes gets much, much smaller. So we get lots of points in the area around where we think the fault is, and many proportionately fewer points in the far field areas where there is nothing going on. So that's great. And we're just going to save this this data so that when we run our next notebook, we can load it into that. Okay, so we have downsampled our interferogram from, I don't know how many pixels this would have originally had, but you can see it's 5,000 by 6,000. What's that? 30 million. If you do that sum, of course, there's not all data in all of that, but still, it's of the order of tens of millions of points, and we've turned it into just under 200. Obviously, it takes a lot less time to run a calculation 200 times than it does to run it 30 million times. So, hopefully our calculations will be much more efficient if we use this data. There is a third notebook or fourth notebook where we just read that in and write it out as files in an ASCII format. I see a question: is downsampling similar to multi-looking? You could argue that multi-looking is downsampling because you're taking many pixels and making a smaller number, and it has a lot of similarities. Of course, the difference here is we're not doing the multi-looking, or we're not doing the averaging over a constant area size. In this case, of course, we are downsampling, but we're averaging over a large number of pixels for some areas and a small number of pixels for others. Whereas if you're multi-looking, you're applying the same sampling to the whole interferogram. Okay, we can load this one in and just flip through a few of these early scenes. And what it's doing, it loads in our Quadri file, it reapplies the Quadri, and it is extracting information, for example, like the coordinate system, the location of the reference point in your interferogram, and converting it from lat long to a local coordinate system in UTM coordinates. Because Ocada uses a rectilinear coordinate system, which is not in degrees, it's in meters. So we basically do that to convert from lat long to meters. This section here extracts the line of sight information for each of our Quadri cells. That's important, of course, because we want to model our data using the line of sight information. And Kite has loaded it in, so we just want to extract the representative values for all of our locations. So we do that. The codes that I use use coordinates in kilometers, so we're just going to sample things into kilometers, and we can plot our data points in our UTM coordinate system now to see if they look right. And this is basically what our interferogram looks like when you plot it as points. I guess I'm using a jet color scheme here instead of the green, blue, yellow one that is default in that plot lib. But you can see, anyway, blue is negative, red is positive. It looks quite nice. Everyone should be happy. And the final step is to write out some files that we can then use in later notebooks. So we do that, we run it, and now we have saved some files. And specifically, we have output a file here that is in a format that contains all the information we need to model these data. So it contains an X coordinate and a Y coordinate, contains the amount of displacement and line of sight, and it contains also the line of sight vector for that point, three components. So again, like 0.65, 0.11, minus 0.74, and last thing is the data point number, and you can see there are 194 data points. So we are ready to try and model this this interferogram. I don't have any time, but all right, I'll try and move quickly. Okay, so this next notebook is called a CARPI forward model. It uses a set of functions that I call a CARPI, which is a CADA in Python. It just does a lot of the things I showed you at the beginning, but behind the scenes, all the coordinate transforms and all that business. You import these things, happily imported. We load our data file in and show us now we've loaded our data in as a NumPy array. So it's got 7 columns and 194 rows. And I'm just going to use a sort of a guess of what I thought the earthquake should be in terms of its strike. I'm going to say 60 degrees, its dip 90 degrees, the rake 5 degrees, slip 2 meters, the coordinates of the center of the fault in XY. I kind of eyeballed that from looking at this deformation pattern. You know, you can see a point somewhere in the middle here would be approximately where the fault center would be. So you can do that just for a guess. I could say like 495 kilometers and maybe 4240, something like that. You don't have to get it right just away. Okay, yeah, you see 495 and 4238, a length of 25,000 meters and a top and bottom depth from 4,000 to 12,000 meters. The reason I'm using, I'm burying the fault 4,000 meters down is because you don't see a sharp discontinuity in the interferogram. There is a kind of a zone of low displacement between the high negative and the high positive, which means that the fault didn't rupture all the way to the surface with its full amount of slip in this case. And we have our elastic parameters as before, the 2 Lame parameters, 30 gigapascals each. So you can run that cell. And with this what we call fault parameter information, with the elastic parameters, and with the data, we can run this function called rectangular shear fault that will calculate a series of model displacements for all the data points that we fed it. And we can plot that and see what we get. And my first guess, and it was a complete guess, this is what the displacement field looks like. It's not too bad. I mean, maybe I've got a few things slightly wrong, but if I was going to use this as kind of a starting guess, this isn't too bad. You can see I get the right sort of sense of motion, negative in the right place, positive in the right place. I get the orientation of the pattern more or less right. It's not bad. And of course, you can calculate how well it fits your data. And so what we do here is we take the data values at each point, and we subtract from them the modeled values for each data point. We square the difference because that would make it always a positive number, and we add them all up for all the points. And so we call this value the total squared penalty. And when you run it, I get a number of 0.433 meters squared. And that's, on its own, it's hard to say what the significance of that number is, but obviously the lower you get this number, the better. So we're going to try a bunch of models and see if we can make that number smaller. The next point to make is that as people asked earlier today, we don't actually know what zero displacement is. We kind of assume that far away from the fault should be zero. We don't know that for certain, which means that there may be a shift that you can apply to the whole interferogram that would make it fit better. And so in this case, we're just going to figure out what that is and remove it from the data and then recalculate the misfit. And when you do that, you would shift the whole interferogram 2 centimeters actually to make it fit better. And then when you do apply that, you actually get a total squared penalty that's slightly smaller, like 0.357. And the final thing we do here is just to show you what it looks like when you subtract the model from the data and plot it. We call that the residual. Of course, you've met that already on Monday when we were using a Mogi source to model a volcano. And you can see that this complete guess of mine, it fits the data well in some areas. You know, you're looking for values around which are green on this plot. These would be close to zero, but I'm overfitting the data in some areas and underfitting it in others. It doesn't fit perfectly. So the final notebook we look at actually tries to find a solution that fits the data using an algorithm that searches for it rather than just doing it by hand. In theory, you could go through and say, okay, I think I've got the rake wrong. It's not 5, it's, I don't know, 20. I don't know if that will help, but you could rerun all these things and see if it fits any better. And it fits worse. I think. Looks like it fits worse. Yeah, my penalty is now worse. So okay, well maybe I won't use minus. I won't use 20. I'll use a lower number. You could do that by hand, but that would take a long time. What we're going to do is get the computer to do it for us. So the final notebook is called Akapi optimization. It uses some of my Akada functions. Again, adds another one which calculates what we call a penalty function, which is basically the misfit in one go. So we're going to load some dependencies. We're going to load in our data. Remember our file that has the displacement of every point and the line of sight vector for every point. And I'm going to input a bunch of starting parameters. These are very similar to the ones I used before. I'm also specifying some uncertainties for each of these parameters. So for example, our strike is 60 degrees, but I'm going to allow it to vary by multiples of 10 degrees. So I actually am going to let these vary by 2 sigmas. So if I use a sigma of 10, that means the bounds are plus or minus 20. For strike, dip bound of 15 means I'm going to allow the dip to vary plus or minus 30 degrees from vertical, and so on and so forth for all these things. So I make vectors out of these. I calculate the upper and lower bounds for all of these using just 2 times the sigma and as the upper and lower bounds. And I also find a random model that's somewhere between those bounds, and I call this the restart parameters. I make sure here that the parameters for the things like top and bottom of the fault, make sure the fault's not upside down, that the top is above the bottom. That's a sanity check in our parameters because we're using random numbers, and I output at the end what my starting model might be. I guess I can disable scrolling. Cool. Okay, so my starting guess for this model is a strike of 59 degrees, a dip of 119. So it's actually dipping the other way. It's dipping greater than 90 degrees, means it is dipping 71 degrees the other direction. A rake of 40, a slip of 2.8, and et cetera, et cetera, et cetera. I'm going to specify some elastic parameters. And calculate the penalty for my starting model. And this is also a bad starting model. 0.84 is worse than my first guess. If we get to here, then we're going to specify, we're going to set up an optimization. So we're making use of the SciPy packages, which is a series of scientific computing libraries that have been developed for Python. One of them is an optimization function. And what that means is you give it, you feed it the Geocoded model, which is comes under this function name LOS penalty fault, which takes as its inputs some fault parameters, the elastic parameters and data, and tell it that it can manipulate the model parameters according to some scheme that's built into the function to try and make that penalty function get smaller. So that's what is going on here. We're minimizing the function minimizing the function LOS penalty fault using the values in our fault parameter function as a starting point, and bounding the variables using the bounds that we specified. And if you run this thing, it goes away and thinks about it. And in a minute or less, it will come up with the answer that it thinks is best for that starting model. And we're using a Powell algorithm to do this. And a Powell algorithm is a downhill method. The way to think about this, I guess, is if you think back to what we were doing with France on Monday, when we were looking at the penalty function, and it looked a bit like a surface. You plotted it in 2 dimensions, and you had high values and low values. It's trying to find the lowest value by varying fault parameters. It will start by changing one parameter and seeing if the misfit goes up or down. If the misfit goes down, it keeps varying that parameter until it gets as low as it can. And then it will try a different parameter and vary that one. And it keeps doing that until it finds the lowest penalty that it can find. And when it does that, when it finds that, it stops. So it ran, I think. We can run the next cell, which gives you results. And this is what you come up with. So it tells you the directions that it was trying to move in. It's in parameter space. Maybe we don't worry so much about what those mean right now. But what it tells you, other things, it tells you the best penalty function, best value of the penalty that it found. And if you remember, we started with a penalty of 0.846. And through a bunch of iterations, it found a penalty that's 0.109. So this model should fit the data way better. It did that by iterating 7,300 times. So it's not necessarily a surprise that it found something better, because it spent a long time working at it. And it outputs here the parameter values that gave it this misfit. And if you want to parse what these mean, then you can run this cell and it will tell you, the strike is 59, the dip is 98, the rake is -14, the slip is 0.74 meters. This is the location of the fault. This is the length of the fault, top and bottom extents, and so on. So the initial penalty was 0.846, and the final penalty was 0.109. So let's see. So this shows that the optimization found a better model than the one it started with. That's good. But the reason that well, I should backtrack and say this may not be the best model that's possible. If you run it, you probably get a different answer to me, because it uses random numbers, and those random numbers might give you a different answer in terms of the starting model. And the reason that we would try lots of different starting models if we were doing this is because imagine if it's a downhill method and you're trying to find, for example, if you're trying to find the deepest crater on the moon, you might use a similar method. You start in a place, you walk downhill until you get to a point where you can't go downhill anymore, and you will find the bottom of a crater for sure, but you don't know necessarily if that's the deepest crater. What if you find a deep crater, but there's an even deeper one just beyond? You wouldn't get there from your starting point following the rules that you do. But if you started somewhere else, you might find this way to a deeper crater. So in these methods, we like to try many random starting locations, and hopefully one of those will get you to a model that is better than that is the best model, the optimum model. Because there's about 70 odd of you on this call, we kind of have already done that experiment. We've already run it a load of times, if you've been able to run it. So what I propose we do is paste our solutions in a spreadsheet. So I'm going to show you, I guess, this spreadsheet. I'm going to put penalty in the first column. I'm going to put name for you, and I'm going to put parameters in the third column. So I'm going to get my best penalty, which is 0.109 blah. I'm going to copy it and paste it in here. I'm using row 1. My name is Gareth. And my parameters are these numbers here. I'm going to copy those. Hang on, maybe backtrack. There's a better way. Copying the parameters. Maybe I will make a code cell here. Paste that into one long string. I think would work better. Like that. Copy and paste it in here. Cool. So those of you who have a model, paste them in here and we'll see how many models we have, and if anyone can beat my 0.10905, I see a 0.10904 already, so I am not the winner today, but maybe someone else.
You're doing pretty good, Gareth, though. You're pretty close.
I'm in the top 10% or something.
1090. Brian looks good, I think. Ooh. No, wait. Yes, Brian's still in the lead. It's very tight.
Yeah.
Brian and Alex are almost the same.
Or whoever 0.10903 at the bottom there, Residual. That might be the clubhouse leader now.
Oh yeah. Wow.
Can we get your parameters? Exciting. What we have done here is basically parallelized the whole inversion. So we're running lots of versions at the same time, which I've yet to do for the code.
Crowdsourcing.
Crowdsource the modeling, yeah.
There's a question, how do I go back to find the parameters I missed?
How do you mean?
Yeah, so
Your
you find
best model parameters are here. This string of numbers. And I just copied and pasted. I made a new cell by clicking at the plus button, and I pasted all those numbers into one long line and copied and pasted that and stuck it in the in the spreadsheet. And so yeah, it'd be great if our current best model could do that, so we get all the parameters. And preferably as that number string, because it's easier.
I think the leader has not changed, right? So
No. We need all the numbers to reproduce your model.
Radula, if you could, instead of taking what you put in here, if you take the string output from the cell ahead of that,
Like these.
or we can just, yeah.
So what I did, I copied this thing and then I pasted it into this cell here. So I can do that again just to show you. I hit plus and you get, I want to do it here. I hit plus and I get a new cell, and I can copy these numbers with Control C, Control V, and then I just took out the returns. So they come as one. You can paste them on one line when you do that. Copy, paste.
Yeah, so whoever has the name Radula, if you could do what Gareth just showed, and repaste your parameters one more time, because I think you're still leading.
Well, that looks like the best model, doesn't it?
Yep, I think it still does.
So you can copy this. It's not ideal. Paste that and take out strike. Dip. Break. length, top and bottom, and copy that. So let's see. Paste our best fault parameters in here, like that, and our best penalty. Go back and copy your penalty number. That's that. Paste that in here as well. Then if we run this and then run this, we can plot to see what the model looks like. And it looks really good. So this is the data that we started with. This is the modeled result, showing the fit of that model to the data. I mean, you see blue in the same places and red in the same places. That's pretty nice. And then when you subtract the model from the data, you get this residual here. So there are still some details that we're not fitting, but that's probably because we're only using one rectangle to model the whole fault. And there could be some variations in the amount of movement on that fault in different places, and that could easily explain why we don't see a perfect match. Plus, you can see there might be atmosphere and other things in here. The far field displacements are different and have some variation there. But overall, this is a pretty good model. And this kind of thing is how you would go about trying to make one of these models. The last thing is just showing what you would do if you wanted to do this on your own, rather than asking like 70 of your friends to run the model at the same time. What you would do is you would loop over many different starting locations, which you select at random. I'm going to say here, we're going to do this 100 times. I'm not going to run this now because it will take a long time. But you could do the same process, but just start 100 different models in random locations and pick the best one at the end. And that's basically what we've just done with all of you guys. And you just loop through, and at the end, you save the model that has the best model parameters, and you track through here. 0.1093033 is what I got last time I ran this, which is very similar to what this misfit is for this model.
Gareth, I think some people have issues with copy pasting the parameters and finding into the cell above that. Can you just practice this one more time? Where you found those parameters and how you copy pasted them in.
So I took Radula's parameters. I deleted all the words from the line above. So this string of numbers here is the best fitting model. So I copied that. I went into the copy optimization thing, and I pasted it into best F params like that. And then I also went back and I copied their penalty number, which is on the left here, and pasted that as the best penalty. That's more or less for your reference. Once you've done that and run it, then you can calculate, you can plot the model result. And that is how you model an earthquake from INSAR data. You take the data, you quadri the data, you might come up with a starting guess for the geometric fault parameters that you need to match the data. And then you use those starting guesses, specify some bounds, and you run it through an optimization algorithm to try and optimize the fit between the model and the data. And that's basically what we do when we model earthquakes. That's all the tricks of my trade in just over an hour. I ran over time though. My bad.
And congrats to the winner.
Yes, Radula, you win the prize of the recognition of your peers. I don't have any t-shirts or anything to give away.
Do people have more questions about this process?
yeah, I can now stop talking and actually look at the chat window maybe. This is the lowest misfit. These are the parameters that go with that lowest misfit.
Can you maybe speak about why we needed to put in an initial guess for this problem and how close you feel like the guess should be? If you catch my drift, it's like
Yeah, I mean, so these methods, they iterate based on, they try and change parameters, but you need to start somewhere to do that. So you need to have a guess of a starting parameters, which is in the neighborhood of the right answer. I mean, as you'll see in this notebook, at the top, we set bounds for some of these things like sigmas of 10 degrees, 20 degrees, and so on. If you're unsure of how good your starting model is, the thing you can do is to make these bounds quite large, and then that encompasses lots of possibilities. And you can run this optimization with the loop at the bottom more than once. If you know it zeroes in on a solution, you can use that then as your starting solution for the next go round if you like. You can paste your best parameter values in here and try again. But yeah, the secret is that it selects random starting locations within the bounds that you specify. So making sure that those bounds are sufficiently big that it captures the range of possible models. And this is a trial and error process. Often if your model converges to an answer that doesn't look very good, or it's hitting a bound in the model, and I think ours might be close to a bound because the fault lengths are getting quite close to 29 kilometers. You could make the length bound longer and see if it improves your fit, for example. Those are things that you would look at in your final solution. Can we use these parameters but decrease the best penalty value? No, that's not really what's going on here. Those parameters are associated with a best penalty value. If you pasted those values into this notebook where we just calculate the misfit based on a model, then you would get the same. You should get the same penalty, which is 0.0103 something. That's mostly for your information, but also that is the penalty that goes with these parameters. If you change any of these numbers, you would also, when you run it through the model, you would get a different penalty, and it might not be better than this one. And in general, how do you guess what the parameters, the starting model should be? Well, I started, I guess, looking at, this is the data, the plot of the data that we got from the start. And I kind of eyeballed where the middle of this pattern was for the location of the fault. I eyeballed the kind of the angle that you get when you look at that pattern. It comes through like that or something. I guess that might be 60 degrees from the north. If you have other information, for example, from seismology of what some of these parameters might be, then you can use that to guide your choice of things like the strike and the dip. Could I go over the importance of zero shifting again? Yeah, okay. So what we did was we ran a model and it looks like this, for example, on the penalty was 0.81, right? Around that. We don't know what 0 is in this case. We're assuming that somewhere far away from the earthquake there is 0 displacement, but that may not be true. So what we do is we calculate what the average difference is between the data on the left and the model on the right, and we subtract that away, and that should bring the model into better alignment with the data. So we just subtract one number from every data point and see if it improves the fit. And we start with 0.81, and when you subtract the average, in this case, it doesn't help quite as much as before, but it still reduces the penalty by something if you do that. And when it comes to running the model, actually that is automatically done in the next notebook, that we automatically remove the shift as part of the model, because if that shift is very big, it could add a large amount of penalty to the penalty function that isn't really real. It's as a result of this 0 level shift, not because the model fits well or badly. We're just trying to fit the shape of the data. And Eric says he's worked on this earthquake, which is cool. We should compare our results. Silence out there. Any more questions, or can we have a break? I'm happy to answer more questions on this in office hours, or tomorrow morning, or on Slack. But I should probably stop talking and drink some water and eat some lunch. Anyone else? Anyone else feel the same way? It seems so. We've come to a standstill. Okay. In which case, we should come back at what, 12:30? Any of my fellow instructors want to chime in? 12:30? Yes. Okay. 7-minute break. See you all in a little bit.
Garrett, and is it the time series theory?
Yes, next.
Okay.
Oh, good to hear from you. I haven't seen you in a while.
Busy time.
Yes,
Well,
I imagine. Sorry for overrunning. We'll get to you in a little bit.
I just meant to remind you.
Oh, it's fine. I know you're supposed to be here. Haresh Patahi, everyone. Okay. Welcome back, everyone. So the next session is going to be about INSAR time series. And we have Haresh Fatahi here, who was involved in a lot of the developments of the notebooks you've been looking at today and in other days. And he's going to lecture on time series and some of the theory behind them.
Oh,
So,
all right.
when you're ready, take it away.
Sure. Thanks, Garrett. Let me share my my slides. All right. So okay. Okay. Do you guys see the right screen?
No, we have the presenter view.
So, is this
There
the
you
right screen?
Yeah.
All right. Okay, so hello everyone. My name is Haresh Fatahi, and sorry this year I haven't been able to be involved too much. Very busy time for us at JPL with NISAR and other projects. I hope that you guys had a great course so far. Today I'm going to talk about the theory of the INSAR time series analysis. And so I have just some slides here. A copy of these slides I uploaded to the GitHub and issued a pull request, Paul. So if I don't know if you merged it, but if you merge that, so everybody will have a copy of these slides as well.
I didn't, but maybe somebody else did.
Yeah.
Yes,
but
it's merged.
Okay, so for now it's not needed really. Hopefully, yeah. Okay, so before I start, I would like to thank my colleagues, Sarah Mirzai, Yunjun Zhang, Yuji Zhang, Piyush Agram, Falcon Milong, and other colleagues at JPL, Caltech, and University of Miami have contributed to many of the works that I'm presenting today. What I'm going to talk about is just, I know my colleagues, Paul, Franz, Eric, Garrett have been talking about INSAR last few days. I will just an overview one slide, and then I'll jump into why we do need to do the time series analysis. And then I will get to the different ways of doing the INSAR time series analysis. This really can be a course by itself for a semester, as Paul says for other materials too. But I will try to go through it in a short time. And then no matter how you do the time series analysis, I think there is one mic open.
Eric, I think.
Okay, and then no matter how you do the time series analysis, we are not seeing only the ground displacement. There are other things in our time series. So I will just give a quick overview of those as well. So just a reminder that we have INSAR, and we are measuring some differential phase called interferometric phase between two SAR images. In an ideal case that we don't have other contributions, we have two SAR images, and let's say ground has moved due to an earthquake, and the phase difference is basically representing the ground movement. However, the truth is that this interferometric phase component has many contributions. It has, of course, the interferometric phase due to the ground displacement, as well as due to the atmospheric delay, because our microwave signal is propagating through atmosphere with different layers, including ionosphere and troposphere. And we have some geometric phase. Basically, imagine if you have two orbits, and the first orbit here, the second orbit here, and we are measuring some data from the ground. If nothing is moving, if there is no atmosphere, just because the orbit is different, the range from the radar to the target from the first image is different from the second image. So there is some geometrical phase there that you guys probably have seen in the previous presentations. That's why we do, for example, topographic phase correction and flattening and all that. There could be still some residuals left if the DEM is not accurate enough, or if the orbit is not accurate enough, or some other reasons. We could have some geometrical residuals left. And then there is the ground itself, the scattering properties of the ground, even without solid earth movements. The scattering phase could be changing, and that could introduce some phase, some interferometric phase actually. And then there is noise, just because of, for example, the correlation, which I'm sure that Paul has talked about all that to some extent. So the magnitude of these components in the interferometric phase of individual interferograms that we are getting is roughly, for displacement, is usually millimeter to centimeters, unless if we have a big signal like an earthquake or volcanic eruption. But for most of other signals, like driven by tectonics, hydrological induced subsidence, uplift, tides, or volcanic activities, we usually have much smaller. However, on the other hand, the noise could be large. The atmosphere is usually centimeter level to tenths of centimeter. I'll get to some of that. The geometrical residuals could be a couple of centimeters. And the scattering phase itself could be some millimeter level, if not centimeter. So we really need to do some time series analysis to get rid of some of these noise components and get to the signal that we are interested in. So to summarize, why we do INSAR time series analysis, I can think of three main reasons. One is to beat down the impact of the decorrelation. So the scene that we are taking some data from is changing over time. Next time that we are talking about rapid path interferometry. So next time that we visit the same area, a lot of things could change. It could be just the ground was dry and now it's wet, or it could be the vegetation has grown, or some vegetation has been removed. So there were not buildings, now there are. A lot could change. Here is an example on the left that it was some terrestrial X data over Bay Area in San Francisco, 2.5 years apart. A regular interferogram would look like this. It's all noise. But if we do INSAR time series analysis, the same pair would look like what you see on the right side. So it's almost after the magic that I'm sure Paul has this nice slide, that the magic of interferometry, that you have two SLCs that it's all noise and random phase. Here is another kind of magic that with time series analysis, we are filtering some of the correlation noise. So that's one reason to do time series analysis, to reduce. Of course, it's not always this dramatic. We have a lot of pair interferograms that look very good and we can use them. But this is the extreme case, just to really emphasize that there is some temporal decorrelation of reduction through the time series analysis. The other reason to do the INSAR time series analysis is to improve the accuracy of the estimated displacement signal. The interferograms, as I mentioned before, are dominated really by atmospheric delay with different components from ionosphere or troposphere. Here is a example from Yunjun's paper a few years ago that we have one interferogram over Galapagos Islands that you see that the Galapagos Islands are well known with a lot of volcanic activities, but looking at one interferogram, it's just ionosphere actually and some troposphere. But if we just take hundreds of these and do time series analysis and fit a line to the time series, we get this nice velocity field where we have isolated the displacement signal where the volcanoes are. So besides the decorrelation noise, there are other sources of noise that are actually spatially coherent, like atmosphere, but they have a random nature in time. So if we do time series analysis, sometimes even without correcting for them, just by having a lot of data, that random nature of the noise through time helps us to reduce the noise and get more precise displacement time series. The other reason that I can think of why we should do time series analysis is very obvious. A lot of signals, the ground displacement signals, could be non-linear in time. So just really looking at only a pair of interferogram is not going to tell us how the movement of the ground is evolving through time. A good example is just the earthquake cycle. During interseismic period, you have almost a linear strain accumulation. So the movement of the ground is linear, and then suddenly you have the earthquake. So you have a jump here, and then you have post-seismic deformation. I'm sure Garrett has talked about all this, and we really need to look at the time series to get a very clear picture of what is going on. Earthquake is not the only example. There is volcanic activities, very nonlinear deformation. There is seasonal groundwater change that we really need to do time series analysis. All right, so we want to do INSAR time series analysis. There are many ways these days to do INSAR time series analysis. In my view, we can start by just classifying these algorithms based on the scatterers, the type of the scatterers that we have. We have a resolution cell in our SAR image, and that has one value, but that is not coming from one scatterer. That resolution cell, let's say for Sentinel-1, it's 2.4 meters in range direction and 15 meters in azimuth direction, roughly. So there could be a lot of things in that resolution cell. If the resolution cell has many scatterers, almost similarly, they are contributing to the return of the signal. We usually call that distributed scatterers. But on the right side, I'm showing a case that the resolution cell could have those. There are always some scatterers, but there is one that is dominant, and that is contributing most to the return signal. That's called permanent scatterers. So usually in nature, wherever that you have, if you look at the park or some agricultural areas, natural land, let's say that's usually distributed scatterers. In urban areas, when you have a building, or even in nature, when you have rocks, those are actually permanent scatterers. So just based on those two types of scatterers, we have two groups of the INSAR time series analysis techniques. One thing that to note here is you could imagine, without going to the details, you could imagine that if you have a permanent scatterer, basically that strong return also leads to more precise phase measurements through time. This is a cartoon, really, this is not real data, but that's what we would expect. However, for distributed scatterers, there are many scatterers, and things might change randomly. actually, if they change very randomly, so we cannot do interferometry, or if we do, it would be noise, the interferometric phase. But if they are changing more and less similarly, then there is still coherence, and we do interferometry, but the phase is not as accurate it would be for a permanent scatterers. So in general, there is that accuracy difference between the PS pixels and the DS pixels. So let's take a look at the PS algorithms. Permanent scatterers time series analysis algorithms goes back to the Ferretti paper 2000, where they proposed this relatively simple algorithm for time series analysis, where we have a stack of already aligned SLCs, so it's not anymore a pair, but a stack, hundreds could be, or tens of SLCs, that then they are all aligned on the same grid, and you would look at the mean and standard deviation of the amplitude of those SLCs, and you compute a metric called amplitude dispersion. And this amplitude dispersion can help us to identify where are the PS pixels, because PS pixels are those that overall have a high backscatter, so mean is large, and they are more precise, so they have actually the variation through time is smaller, so sigma is small. So overall amplitude dispersion in areas that is smaller, it's more likely it's PS pixels, and if it's larger, it's most likely DS pixels. Once you identify the PS pixels, then you can make interferograms between all different acquisitions that you have compared to a reference acquisition. That's a single network, single reference network of interferometric phases. And then once you have that, so you have a lot of interferograms or wrapped interferograms relative to a reference image, then you can just basically unwrap them, and you already have a time series. So this has been what the original PS algorithm was, and of course after that there has been different flavors of that, more or less. One thing that there has been a lot of work on was how to identify those PS pixels. Is the amplitude dispersion really enough to identify PS pixels? That was the work from Hooper et al. 2007, and that went to stamps that, we probably need to look at phase as well, and come up with some criteria about the phase stability. And of course, tons of other papers that are around about how to identify PS pixels. All right, so no matter what, when you have done that, the amplitude dispersion actually remains as a strong criteria to identify PS pixels. Here is an example. On the left, I'm showing just the background optical image from Google Earth over North Miami Beach. And in the middle, I'm showing the amplitude dispersion. And on the right side, it's the same map, but I have thresholded with a threshold of 0.42 to identify PS pixels. Just with that simple thresholding, just note that wherever we have water, the amplitude dispersion is large, so that cannot be PS pixels, right? And wherever we have most likely PS pixels, they are mostly in the urban areas that we have point targets. So if we threshold that, we already get the candidate PS pixels. Here is an example. If we go run through all the chain, of course, with not exact original PS algorithms, but this is the final PS displacement velocity map. After you have the displacement time series, you fit some line to the time series, and you get to the rate of the displacement. This is over North Miami Beach. It was originally reported by Sarah Mirzai. She has a paper in review. We did similarly with different tool, but similar algorithm at JPL recently for some other projects. And here's an example that you see the PS pixels are in the buildings, and there is some area that is already documented by Sarah's work that they are subsiding. That these are big towers built in North Miami Beach that actually they are subsiding. The building that collapsed was a little bit south of this study area, so it's not in my area. But yeah, so this is what it would look like. However, the PS analysis, PS time series analysis, has its own drawbacks and challenges. The main challenge is that we don't usually get that much PS pixels everywhere. Of course, in urban areas, we get a lot of PS pixels, but in natural areas, it's challenging to get PS pixels. Here's just look at this golf course. Even in North Miami Beach, it's an urban area, but it's golf course. So we get PS pixels only over the buildings. So a lot of the natural area, well, the golf course itself is missed. That's a big challenge for phase unwrapping, that really has been a drawback since beginning for PS algorithms. Just to give you a little bit more idea about that, here is a map over the Concord Fault, where it's north of Bay Area. There is a fault going on. There's a fault here that actually it has a signal. My colleague Katya Timofeyeva discovered this creep signal here. Regardless of the interesting signal, but just look at the distribution of the density of the PS pixels in this map compared to this map on the right, which has both PS plus DS pixels. Whoever has done even one time phase unwrapping would agree with me that unwrapping the one on the right should be much easier than unwrapping the one on the left. It's just simply there are more pixels and the algorithms behave better. Otherwise there should be a lot of assumptions how to unwrap this. So that gets us to look at the DS pixels. We cannot just ignore the DS pixels. They might not be as precise as the PS pixels, but well, there is a great value, at least for phase unwrapping. So that's why that very short after the PS algorithm, actually there was the DS algorithm. The first one was the small baseline algorithm. I'm sorry that I don't have a citation here, but yeah, that would be the algorithm from Berardino et al. 2002. The idea is that we have a stack of SLCs aligned and we make interferograms. We make small baseline interferograms because we usually the correlation, the amount of the correlation increases with time. So if we have interferograms that are closer to each other, usually in time, they are more coherent. So the idea was, and also for old missions like NVSat and ERS before Sentinel-1, the orbital tube of the missions were large. So we had kilometer scale baseline between the orbits. And that would also cause the correlation. So the idea was makes very small baseline interferograms, small baseline in space and also in time, and then just unwrap them and form this system of equations. You have for each pixel, you have the vector of the interferometric pairs, and you can form a design matrix that relates the time series phase to the interferometric phase. So this is our observations, interferometric phase. We make the design matrix, and we are inverting for the phase through time, or the phase time series, which is really a single reference interferometric phase in my opinion. So just based on how the residual of that inversion would look like, you could come up with some metric called temporal coherence. Yunjun is going to go through this algorithm more in detail in his presentation, I think tomorrow. Anyways, at the end, you get to some from pairs of interferograms, you get to some time series, which could be representing really at least range change through time, including of the ground displacement change through time. So this would be the ESPAS algorithm. As I mentioned, just to emphasize that there is a network of the interferograms that basically in this network, each line, each circle is one acquisition. The x-axis is time. The y-axis is the perpendicular baseline. That's a component of the baseline between the orbits. And as you see here in this network, each line is one interferogram. And the interferograms, you don't see an interferogram between the first acquisition and an acquisition at the end. That would be too long in time, and it would decorrelate. So ESPAS algorithm usually, at least the original algorithm, was avoiding that to get to very coherent pairs of interferograms. And then you invert that. That was the inversion that I talked about in the previous slide, and you get to a single reference interferogram. So that would be basically the time series. Of course, after the original ESPAS algorithm, okay, now I have the citation here, there has been many other papers and modifications to the algorithm, but really the core is still the same. It's just about having preformed interferograms, unwrap them, and invert them to get to the time series. The time series notebooks that Yunjun will talk about them tomorrow are actually based on this algorithm as well, and he has documented that algorithm. And of course, a lot of modifications have been applied to it. But again, the core, in my opinion, it's still the same concept. Colleagues all around the world, including ourselves, we have used this algorithm to measure ground displacements over local areas or over very large areas. Here is what I did during my PhD around 10 years ago. I'm getting old too. And here is the plate boundary between the Indian plate and the Eurasian plate. There is this fault system called Chaman fault system. It's in a remote area compared to what we usually are used to, for example, in California. So really, remote sensing is the best technique to understand this fault. And there was not much study at the time. We used NVSat at that time using ESPAS algorithm, making a lot of interferograms, invert them, and get to some displacement time series. And here's the rate of the displacement time series. One of the discoveries there was the fault creep in parts of the Chaman fault there. There are a lot other signals, hydrological signals, and again, you can look at the literature, and there are many publications showing that how ESPAS algorithm has worked successfully, actually, in comparison with GPS and with other data sets, especially when there are big enough signals, especially with older data sets. However, so far so good. Happy with the ESPAS as well, and distributed scatterers. But just recently, after the launch of the Sentinel-1, there has been some concern about the distributed scatterers time series analysis based when we use only a limited number of interferograms or small temporal baseline interferograms. Here's one plot from Ansari et al. That came out a few years ago. On the left, you see the velocity field somewhere in Italy, southern Italy, where the ground deformation is well known. There, how should it look like? And if you use only 5 nearest neighbor interferograms in your network and do time series and look at the velocity, you get this one. If you use more interferograms, 10 nearest neighbor, you get something different. And if you use all possible pairs, you get all that red is gone. And what you get is very similar to what the PS time series would give you. So this they argue this is a proof that the distributed scatter time series analysis with only small temporal baseline is really could be dangerous, and unless if you use a lot of interferograms or possibly all possible pairs. We actually looked at the details of this observation. They really didn't talk about what is driving this in that paper. So our postdoctoral scholar at JPL Caltech, Yuji Zheng, did an amazing job looking at the details. And we have this paper. You can look at the details. I'll try just to highlight the important parts. We have demonstrated that bias actually is caused by the closure phase. That means that if you have three acquisition dates, 1, 2, 3, or IJK, you make an interferogram between I and J, and between J and K, and then between K and I, they actually should close. That's the closure phase, and that should be 0. And usually it is for single look interferometric phases. But as soon as you do some multi-looking, you start seeing non-closing triplets. So this is really this violates that SPAS time series analysis, or any actually, not only SPAS, any time series inversion, because the intrinsic assumption for any time series inversion is that this loop should be 0, even though it has not been clearly mentioned in many papers, including old papers. But that is the intrinsic assumption, that those interferometric pairs are consistent. If they are not, well, that's closure phase, and that causes the bias. Why this happens also, we looked at some details and some simple models to explain why it would happen, why multi-looking would cause this. A simple model that we came up with is, you have a window that you are averaging your distributed scatterer pixels. Just remember, maybe I didn't make this very clear. At the very beginning, when I showed you the PS and DS pixels and the phase through time, the PS was precise, DS was noisy. If we want to use it, because we know there is value in looking at the DS pixels, we have to multi-look. We have to reduce the noise. And here is a multi-looking window. But those pixels may not be all the same. They might, some of it could be bare ground and some of them have vegetation. Or even if it's bare ground, some of them might be wet, some of them dry. So there is some different scattering. And we know all that the radar backscatter is different if you are looking at wet soil versus dry soil or versus vegetation. So all that inhomogeneity in the multi-looking window is what is causing these non-closing triplets, basically. I don't go through all the details here, but the simple model is that we have some interferometric phase model and the expectation value for the multi-looked image. And if you have only two groups of pixel then the multi-looked results, the expected multi-looked phase, is actually the angle of the weighted average or weighted sum of those complex values. So if you have W percentage of wet pixels and 1 minus W percentage of dry pixels, and then if they are changing through time, basically they will cause closure phase, and that will cause the bias. Just to emphasize that actually it's not the spatial inhomogeneity, it is actually the temporal inhomogeneity that is driving these closure phases and the problem with the DS analysis. All right, so almost done with this drawback of the distributed scatter time series analysis. The last thing that I would like you all to pay attention to with this topic is, here is just a demonstration of really what was already in the Ansari paper, that if we use only one nearest neighbor interferogram for the time series analysis over some dry area, it's a dry lake in Mojave Desert, that you would get some signals around the lake that doesn't make sense. It shouldn't be there. There is no uplift there. Of course, there is this subsidence signal, most likely true, but the rest of the things are probably not. And when you use more interferograms, they go away. And when you use even more, they go away even more. And of course, if you use all interferograms, it even looks cleaner. So there is this really phenomena there. And if we look at the cumulative closure phase or the estimated bias, look at Zheng et al. For how to do that, and Yunjun has already added that part to the notebook for MintPy. You see that we have this observed bias that is accumulating through time, and when Yuji looked at the cumulative precipitation, we see just almost a perfect match. So it is really driven by the scattering property changes due to the wet versus dry. And of course, we see that in coherence as well, that was already discovered, but this is really new and very, very interesting. All right, so that all convinced me, and I hope that it convinces you too, that well, we need to look at other algorithms as well for distributed scatter time series analysis. We don't want to just give up on them.
Raj,
yes.
I think there's some good important question. Maybe you would like to address them now. I think it's maybe a lot of people have the same question.
Sure.
For the small baseline, Fateme asked, how good should our processors be for this kind of processing? I guess he or she is asking either we're choosing all possible interferograms or connection 10s.
Yeah, so this is really an active area of research, and it depends really on the different areas. What we have observed in limited areas, connection 1 is dangerous, don't do it. If possible, at least something above 5 so far looks fine, but really depends on the area, and our knowledge is still limited. What I'm more confident about is what that story got me to this slide, that we have to look at all possible pairs of interferograms. I think part of the answer is in this slide. We know that using all possible pairs of interferograms, if we can afford to do it, is the best. But again, it depends on your displacement signal. If your displacement signal is very large, you may not even care about this. Depends on the area as well. So I cannot tell you a magic number of interferograms, unfortunately, but the more, the better. Yunjun, is that can I go on?
Yeah, thank you.
Sure. All right, so we wanna use all possible pairs of interferograms, but that's not an easy job to do. If we do it traditional way, we have to make a lot of interferograms. You guys, you folks, just probably with the StreetMap app and TOPS app, you saw some of the problem. We have big data, and if you have hundreds and thousands of them, life is not easy anymore. All right, there is other ways. Guarnieri and Tabaldini, 2007 and 2008. I really like the credit go back to those guys. They proposed those days that long before we knew about these problems, also they probably didn't know, but they were guessing almost in the paper, if you read it, that yeah, look at the full covariance matrix on the fly, make all possible interferometric pairs. So you have a full covariance matrix. You never have the pairs of interferograms. You make them on the fly. So you have a full covariance matrix. And they are, of course, multi-looked. So if each element of this matrix is one multi-looked interferogram, and the magnitude of that would be your coherence. And then, yeah, then we can think about inverting it and estimate a wrapped phase time series. But during that estimation, we have used all possible pairs of interferograms. So some definitions here, you have the slides, you can look at the details if you want, but really the CIJ is, or C itself is the covariance matrix, and what we call in our terminology, the coherence would be the normalized version of that, and the coherence magnitude is what you guys probably have seen as coherence magnitude as pair, but here you have all possible pairs and you have it for one neighborhood. All right, if we have that full covariance matrix, then how are we gonna get the wrapped phase time series, and how we are gonna basically how to invert that? There are multiple ways to do that. Some optimization algorithms that goes back to the Squeezar paper then, the maximum likelihood estimator, using the, for example, PTA algorithm, that would be Squeezar then. Of course, Squeezar has a little bit more in it. In that paper, they combine PS and DS, but really the DS and full covariance matrix goes back to Guarnieri and Tabaldini paper. But that's one exciting estimation approach there, that you have the covariance matrix and the coherence matrix and the magnitude of the coherence matrix inverted, the inverse of that, and you are solving for a phase series such that this whole basically equation will be the argument of that will be maximized. There are easier ways also to do that, and that would be the classic eigenvalue decomposition approach, which we call CED, following the terminology. Nelson paper with Sarah Mirzai is under review. Previous literature may call it EVD, eigenvalue decomposition, or Caesar by Fornaro et al. In that approach, we have the full covariance matrix. We just do some eigenvalue decomposition, and we look for the eigenvector for the maximum eigenvalue, and the phase of the eigenvector corresponding to the largest eigenvalue is basically the wrapped phase time series already. So, and if you look at that, you see that the temporal decorrelation has been filtered out. Or the same maximum likelihood estimator, but this time, instead of looking at only the covariance matrix, we multiply by the inverse of the magnitude of the coherence matrix, and then we can do eigenvalue decomposition. So the simulations show that this last approach is more precise, but then the drawback is that you have to compute the inverse of the coherence magnitude, which is not really easy to do all the time. It's easy to do, but then there is numerical instability and things can get complicated. And that's why in this recent paper in review, we suggested that, you know what, we do MLE estimate as much as is possible. If not possible, try to regularize it. Sometimes it's possible to regularize and get an estimate. If not, just fall back to CED and provide an estimation. So that's basically the final estimation approach. All right, so this is the story so far for me is that yeah, we still want to do distributed scatter time series analysis because I'm confident about the value for phase unwrapping at least, and for many areas we don't have many PS pixels, so we can get time series displacement time series over DS pixels, and they can be very precise if we do it properly. But well, this is expensive, and we have a live system, for example, from Sentinel-1 already, and hopefully in few years from NISAR, that you have a stack of data. There are areas in the world with Sentinel-1 with 200 acquisitions already. You process something, and a month later, there are a few more acquisitions. So what are you going to do with all that data? Do you want to reprocess them? And even just if it's static, it's a lot of data still. How are you going to do this full covariance matrix estimation? So that's the other paper from Ansari et al. 2017 called sequential estimator. You still do full covariance matrix estimation, but you do it batch processing. You get a if this is the full covariance matrix for a 30 by 30 acquisitions, you get only a part of it, and you do a estimation there, and then you squeeze them to one what they call complex compressed SLC, and then you go on and make more estimation, but really you are dealing with much less data compared to the entire stack of the data. So this is really, the outcome should be very similar to the full covariance estimation. You are kind of going back to the previous acquisitions or a version of it. It's good enough for a lot of data, but it's much faster and it's big data friendly. Just plot of all these different estimators. Sarah Mirzai recently did a comprehensive analysis of all those different estimators, including the sequential estimators. Part of it was done really by Ansari et al. Before, but part of it was not done. For example, Sarah introduced the seasonal decorrelation in the simulations, and that is some interesting results there. That which estimator is doing better overall, and also we introduced the bias, which was not in the original publications. That's temporal dependent, small baseline dependent bias. We introduced that also to the simulations. Sarah has shown that, yeah, as one would expect, the EMI is still the winner, but maybe sometimes not as different as you would expect, depending on the area. What is important is that small baselines again has problem when you have seasonal complete decorrelation. While for other approaches, when there is decorrelation, of course, the phase still, you cannot do magic if there is total decorrelation anyway, you will lose it. But then when it recovers, we can still make an estimate. I think this is my takeaway here. While the small baseline, you cannot do that. So that's one important takeaway there. All right, so this takes us to the final category of the time series algorithms that there is value in PS, there is value in DS, and combining them, and that's the squeezer algorithm that first time was suggested. You have the PS pixels, and you do your estimation chain for the PS, and you get some wrapped phase time series, and then you do DS analysis and DS wrapped phase time series, and then you combine them. The combination is just, this pixel was PS, this pixel was DS, but on a map, then the phase unwrapping doesn't care. It was just some phase, and assuming that you have done your best. Then you unwrap them, and then you have a time series that has both PS and DS pixels in it. All right. We have done actually some of this. This is a work from few years ago. I kind of mentioned this Concord fault, the PS displacement map, and the PS and DS displacement map for a small area. some time series that you see that, you know, there is very strong linear displacement, most likely groundwater. And then there is the creep signal across the fault, these 2 pixels across the fault, very nice creep signal. And then there is this other one that's between E and F pixels, you see nice seasonal groundwater driven signal superimposed on the creep signal. So this is, I was personally very, very excited when I saw this signal. You see it here that the seasonal pattern is jumping up, and that's because you have a creep too. So that's just a demonstration of how these things can be done. We were asked that, can you do these things also for larger areas and earthquakes and all that thing? Those, you know, you have an earthquake, wrapped phase time series, full covariance matrix. Yeah, of course you can. There was an earthquake close to my hometown in Kurdistan, 2017. And I processed just some data there, actually, not just some, 120 co-register SLC, Sentinel-1. It was not full frame, it was around half frame. Doing these things are still expensive to do. A lot of processing CPU is needed. And then, yeah, if you do the time series and unwrap them, you have the displacement time series. You see the displacement plot for 2 pixels. This is differential. The ground was not moving interseismic, or the movement was small enough that we don't see it clearly between these 2 pixels. And then there was the earthquake, and then there is the relaxation after that. If we fit to this, we get the post-seismic signal and post-seismic signal. And of course, when we do full covariance matrix estimation, there is an opportunity to look at the magnitude of the full covariance matrix, and that would be the coherence magnitude. And that could be an opportunity to look at the changes on the ground. Here is one example that due to the earthquake, the same earthquake, there was this city here, Sapol Zahab, that was, there were some distractions there, damage, buildings damaged, and we demonstrated this. Actually, I should have put in, there is a paper that inspired actually by this, by folks at Caltech, Ali, and my colleagues Mark Simons and his group. They worked on this data set actually, and they some neural networks and machine learning for damage proxy mapping. So there is still a lot of opportunity there for damage proxy mapping. All right. So I hope that would be summary of all different time series, different ways of doing INSAR time series analysis. But no matter how we do it, at the end we get to some time series. In our terminology, we call it range change time series. Yunjun will emphasize that as well in his presentations tomorrow. And we would like to say that because that could be including not only ground displacement, but also atmosphere or DM errors or whatever that we have not taken care of. So I will just give a very quick overview of those as well. There could be processing errors. That's something that we should be careful about all the time. I talked about closure phase and non-closing triplets for just coming from the scattering, but there is another way of using those closure phases. If you have 3 interferograms in a loop connected and you make closure phase and look at the integer cycle difference of the triplet, that should also close. And if it's not closing, there is unwrapping error in one of them. Here is a map from Yunjun's paper that you see that he has done analysis of all those stacks of unwrapped interferograms and pixel-wise where the integer closure phases might occur, and that already tells us, at least qualitatively, where the unwrapping errors might be. And I won't go too much details. Yunjun will talk about those. And then there could be geometrical residuals. These days, the orbits are tight. The orbits are very precise. But the DEMS, well, is what it is. And globally, we don't have DEMS that would represent our SAR resolution pixel sizes. We have 2.4 meters slant range resolution with Sentinel-1. With NISAR, we are getting 5-6 meters resolution or bigger. And but the DEMS are maybe 30 meters down, or they have some uncertainties on them anyway. So all days with NVSat, the orbits were large, and this was a bigger problem. Here is one example. If you happen to look at old data or any other missions that, you know, still send TerraSAR-X has kilometer scale baseline diversity. So the errors in the DEM with equation very similar to Paul probably has shown in the interferometric basics presentation, that applies to the time series too. If you have some errors in your DEM, based on how much baseline you have, perpendicular baseline, you get some topographic residual errors. Again, this is more a problem for missions with large baselines, less problem for Sentinel-1, even though for urban areas, again, in Sarah's recent paper, we have shown that you can actually estimate the height of the buildings to some extent. So there could be still in areas that DEM error is a problem. But the good thing is, you know, they correlate with the baseline, and we know how is our baseline, and we can estimate it. The other source of the error is the atmosphere. Here is one old plot that I have. If we have one NVSat interferogram, NVSat had this opportunity to have mirrors. It was optical data, and would give you wet delay. And if you get two of those and look at the difference, it would look like your interferogram, which means that this is completely independent. This is optical data. And you see that all what we were seeing in the interferogram was tropospheric wet delay. Of course, if we have weather models, we can compute the refractivity integrated and get to the delay. Eric, I assume, is going to talk about those, or maybe he has already talked about them. Given the accuracy of the weather models, to some extent, we can reduce the noise. If you look at very large areas, actually, the weather models could make a difference. Here's a good extreme case example. This is pixels few hundred kilometers separate from each other, which I saw very significant improvement in the time series. Don't expect this everywhere. Actually, for small scales, because the weather models are very poor coarse resolution, you don't see this much improvement. But this was just to demonstrate. And then, of course, ionosphere. The tech in the ionosphere is changing. Again, I believe Eric is going to talk about that if he hasn't already, or maybe he has. Sorry, I have lost track of the schedules this year. But yeah, propagation through the ionosphere, depending on the frequency, could generate some delay or phase advance. That luckily we can estimate with split spectrum methods and take and remove from the interferogram or from the time series. Actually, I don't go through the details of that. Again, I assume Eric has either talked about it or will talk about it. But here's one example over Maule earthquake that we had a big earthquake there. And when you estimate the ionospheric phase, then the residual is what you would expect to see from a subduction zone earthquake. Before ionospheric phase estimation, there were all these fringes here. Doesn't make sense really. It turned out to be all ionosphere. And if you compare that time series with GPS, the block is GPS time series. The yellow is the INSAR time series without any ionospheric correction. This is L-band in Chile. So again, this is extreme case. it's not everywhere like that, but this is again for demonstration that how large an ionosphere could be too. After ionosphere correction, you see that the INSAR time series, the green circles match nicely with the GPS time series. All right, so that would be the end of my presentation. I just wanted to, maybe some remarks here that the current and future SAR missions are providing a lot of data, global SAR-C products. Some future SAR missions, including our NISAR mission at JPL, that is planning to generate higher level products. And we have even, you have seen probably the displacement time series products from Europe, and we are doing similar things as well at JPL through Opera project over North America. So there is a lot of data. I think we are converging on what should be the algorithm for the INSAR displacement time series analysis, but dealing with that big data is still challenging, and is an open area of the research, definitely. All right, any questions for me? That will be the end of my slides.
I actually still would like to recall another question. I know Eric answered that, but I think it's a very good one. A person is asking, in an area where there's a volcano and that volcano erupted, what's basically the way to do a time series for in those scenarios?
Right, I will, since you are a volcano expert and you have done a lot of volcano time series, give it a try, please, Yunjun.
Yeah, so I do second all the comments that Eric already posted, and in the case if the volcano eruption is not huge, that means if there's not much lava flow or not much destruction on Earth's surface, then essentially the co-eruptive interferogram, if you can still maintain some coherence, then you can actually do a continuous INSAR time series that is covering that, but that usually applies to a small eruption. And if it's a bigger eruption, like a VI3 or above, usually, then you have to usually cut them into half. I would usually process INSAR time series before the eruption and another INSAR time series after the eruption. And for those two, you can actually usually use the same DEM because as Eric and Harris mentioned, the sensitivity to the DEM nowadays, because of the small baseline tubes of Sentinel-1, is actually the INSAR phase is actually not so sensitive to the inaccuracy of the DEM. So in most of the case, the same DEM from Copernicus or from SRTM will be fine. You just need to estimate this DEM error and its corresponding topographic residuals when you are doing the time series analysis, which we will demonstrate on our last day with MinPy.
Great, thanks, Yunjun. I will just add that would be the flow that Yunjun has been working on so far and has been developing code for, and he will talk about it through the MinPy notebook. I will just add to that with the full covariance matrix approaches, then yeah, I would just go ahead actually and estimate the wrapped phase time series for all of them. And then the trick, all those tricks that Yunjun talked about, will be a little bit less, and then comes back to the unwrapping. That will be what to unwrap, and to be careful with the pairs that have the significant eruption or not. That will be the challenge. If you know, I think the unwrapping is the part that needs care there. Any other questions? That I haven't looked at the chat, so I assume Yunjun, you have looked at the chat and other colleagues. So if there is any other thing.
Yeah, I think that's all the questions, unless Eric or David or Garrett want to add up something.
I mean, there are the last couple of questions, if you want to scroll through and look at them, they're about fringe and how it deals with PS and DS.
I believe all pixels are.
Yeah, one question that is from Xu is about how do we combine the PS and DS together? Are they in the same location?
No, they are not in the same location. So if a pixel is PS, then we don't do any DS time series analysis for it, or even if it has been done, we disregard it. So we give weight to the PS pixels because we believe they are more precise, assuming they have been identified properly. And yeah, so basically we have a mask. We have the wrapped phase time series from DS, and we have a mask of where are the PS pixels. And for all those PS pixels, we use only the PS estimated phase.
Can I ask a follow-up question really quick on that?
Sure.
So yeah, so just to clarify, when you select the DS pixels, that PS mask isn't yet made, correct?
It doesn't matter.
Made.
Actually,
Yeah, it doesn't.
The PS mask can be made at the very beginning, but it doesn't matter.
Yeah, it could be. I think in French how it's set up now is that they are included when the network selection happens. The PS are in there, and then later they're kicked out. Just to clarify.
Yeah. The implementation could be different. In that prototype, yeah, that's how it is. But yeah, as soon as you have the stack of the SLCs and you have the amplitude dispersion, you can basically have the PS. You can know where are the PS pixels.
Yeah. Okay. Thanks. Yeah, I just wanted to clarify.
Sure. Okay. Any other questions? No? All right. So I'll start sharing, I guess.
Thanks, Suresh. So I propose another break, maybe to 1:45. And we'll come back and we'll hear about ARIA, standard interferograms and ARIA tools, which is getting towards generating the inputs to put into these time series algorithms. Exciting. See you in 7 minutes. So next up is Sim Sanger. I saw him very deep
Hello,
on the list. You made it.
awesome. So I'm gonna go ahead and share my screen then. We could just jump right into it. Okay, does everyone see the screen here?
Yes.
Or it's not too stretched out?
You might want to zoom in a bit on your notebook though. That's showing up a bit small.
How do you, sorry, how do you zoom in this?
You can go do it through the web browser, like
Oh, right here.
yeah,
Ah, is that better?
maybe
more?
one or two more.
Zoom in, it's not responding. Okay. Okay, so like, it's better?
That's
Okay,
great.
awesome, great. So let's jump right into it. Let me just start my little watch here. Okay. Hello, everyone. For those of you that I haven't yet met or virtually met, my name is Simran Sangha, but you could call me Sim. I'm an engineer at JPL that has worked with David Becker and Brett and Emre to develop the ARIA tools package that we'll be playing around with today. Note, Brett himself is in the chat and supporting the training efforts as well for the time being, but unfortunately will have to leave at the top of the hour for another commitment. And yes, a special shout out to him, by the way, for vetting and helping cut this year's NAPCO release of ARIA tools. So as we go
Thanks,
along,
Sam.
yeah, of course. So yeah, as we go along, please feel free as appropriate to direct your questions in the chatter show. It's going to be maybe hard for me to see, but if you wish to interrupt or ask questions, that's fine too. But if you attempt to ask me something and I don't respond, it's likely because I don't hear you. So please feel free to try to get my attention, perhaps Slack me. And I very well may have some bandwidth issues and glitches on my part. So that becomes very crucial to try pinging me on Slack if I'm not responsive. I don't realize it and try to make some adjustments my own end. In other words, I'll turn off my video and pray that works. But anyway, so today we're going to be going over a brief overview of ARIA standard products and how we may use ARIA tools to manage, visualize, and manipulate them, and also get them ready for time series analysis through MintPy. But before I get into that, I'll provide some quick background on ARIA and the ARIA standard product itself. So before I continue here, I should lead with the caveat that we're in the process of coordinating a major overhaul of the ARIA website. So what I discuss with you and what you see here will be reshuffled and streamlined a lot in the near future. So stay posted for that. But anyway, as part of the getting ready for NISAR project at JPL, and in collaboration with ASF, we developed a standardized interferometric product that is packaged in a NetCDF format and guided by a file structure as is planned for the NISAR mission itself. So since around 2018, JPL's Advanced Rapid Imaging and Analysis, ARIA project, has facilitated the generation of standardized interferometric products as informed by the aforementioned getting ready for NISAR project efforts. The colloquially named ARIA products have been automatically generated from Sentinel-1 SAR data by leveraging ICE and distributed to open access DACs such that they are available to the community to experiment with and overall get familiar with how NISAR data may look like. So with all that said, let me provide a bit more background on the ARIA standard products themselves that we'll be playing around with. Given what I've outlined before, ARIA GunW standard products are also aptly referred to as getting ready for NISAR products. GunW stands for Geocoded Unwrapped Interferogram, as they are standardized products processed on a frame-by-frame basis and which may contain interferometric layers at 90-meter resolution, such as unwrapped base, connected components, filtered clearance and amplitude, and also a series of downsampled geometry imaging files themselves. So with that all said, let me provide some new exciting updates regarding the current state of production and active areas of development. So under a NASA Access funded effort, we utilize ASF's hybrid pluggable processing pipeline, shortened for HYPE-3, for cloud processing. And up until this year, the archive of ARIA standard products was limited to a select subset of study areas and stood at around 200,000 products overall. But this year, with the HYPE-3 implementation operational, we have been able to expand the archive across many more areas and up to nearly 1 million products, or around 4 times as much more in the span of only around 2 months. And much of that 2 months, too, to be fair, was invested in development and preliminary testing. Now with our routines vetted, we have the capacity to scale up to around 12,000 products per day. In a way, you may be a bit more familiar and comfortable with by now, if not through the end of this week. We may submit processing requests using a Jupyter notebook, which first determines interferogram pairs and then submits relevant information to the HYPE-3 API. Through these efforts, the ARIA Standard Product Archive is now one of the largest and most comprehensive open INSAR datasets spanning continental scales across most major active tectonic and volcanic regions. So if you're interested in more of the details, please check out this main GitHub page for the HYPE-3 pipeline, and keep an eye out for our AGU presentation and also our NISAR poster this coming week if you're around. And hopefully, Brett, if you could share this in the chat, please. So before I continue, are there any questions or concerns so far? Okay, so let's jump ahead. But before I go into the ARIA tools notebooks themselves, let me first show you how to manually visualize and access ARIA products through the ASF Vertex page, this ASF source page, which is a website through which you may access products stored on the ASF DAC. So before you get started, first log in by signing in the upper right here. And then if you want to filter for these S1 INSAR beta products, this ARIA standard products, you would select this option under data sets. And you're going to get something which is a bit deceiving here in terms of this figure of 4.5 million products. Note that unfortunately, we don't yet have these many standard products. Rather, what we're seeing is a duplicative count of by 5-fold of the amount of standard products that actually exist. And you know that by going into filters, under the search filters, going under file type. And this is what I mean by the duplicative counts. By default, it lists each of the individual layers, interferometric layers within the standard product, in addition to the standard product itself. So it's a 5-fold overestimate. So with that said, if we're ARIA tools itself is designed to leverage and manage and manipulate the standard products themselves, even if you don't want all these layers, it's advised that you directly proceed with the standard product itself, as that's what's managed by the software, and you can derive products that way. So you can see that that figure decreases down to 900K products, which is still a good amount, but that's what you have to be careful about there in terms of that deceiving count. But it may be a bit convoluted or so, but so feel free to ask for any clarifications if need be. But just moving on here, as I've alluded to, there are a good number of available study areas for which ARIA standard products exist. And while I have been creating products, we've been creating products across many more study areas. As you navigate this interface, you may very well notice that there's not coverage over your specific area of interest. So this is so far the coverage we've maintained up until today. So that said, since we're scaling up production, if you have any particular study area here that isn't covered, or you're not sure, or you don't see in the ASF Vertex page for yourself, please message myself and the PI of this access effort, David Becker. But it's a little interesting tangent there. But anyway, let's go to just querying products over this particular case study for the ARIA Extract notebook. And that's going to be over the Big Island of Hawaii. So this, the search effort is pretty intuitive. You just click and drag. And make sure to adjust your filter, though, to search for the standard products. And you see there's around 4,000 or so products. But also be careful with the fact that there's a cap placed on what's displayed here, what's listed in the archive. I believe it's the most recent 250 products. So if you want to display everything, you'd have to go here and manually adjust it as so. My bandwidth is already kind of shaky right now, so I'm not going to dare to do that. I'm just going to look at the 250 most recent scenes. And with that said, you could go ahead and click on one of these products, and you have some basic metadata displayed here in terms of the acquisition start stop time, the path number or track number. I'm going to use path and track synonymously here. For this case, it's track 87, this descending track 87. So you could very well from here go ahead and download your product directly, add it to the cart, download in bulk. But keep in mind that you will have to then manage the standard products on your own end. In other words, code up a way to extract the layers you want, crop them and mask them how you want if you want to do that, access geometry information and stitch frames of a given acquisition where necessary. Fortunately, this doesn't have to be your thesis effort. Our team already went down that road for you, and that's where ARIA Tools comes into play. So I'm going to transition to just a little bit more background for the ARIA Tools itself. So it's a quick synopsis. ARIA Tools is a suite of open source tools which automate the post-production manipulation and management of a collection of standard INSAR products for a given study area up through the production of time series. Products such as DEM models, water body masks, average coherence rasters, and qualitative figures of metrics such as perpendicular baselines and spatial extents of product frames are efficiently downloaded or produced and organized through an accessible command line interface. So these tools are again developed, maintained, and contributed to by many people with us here today, such as fellow instructor Brett and Emre and Yunjin, Eric Fielding as well, and also others in the course such as that were not able to make the course, such as David Becker and Rob Zinke. And then just one little last thing here in terms of GitHub pages. As a complement to ARIA Tools, we have documented separate scenarios for each of the tools in a series of dedicated aptly named notebooks found under the Jupyter Docs subdirectory. And they correspond to 6 distinct programs within ARIA Tools, and I'm going to briefly summarize them now. ARIA download, as you'd imagine, is used to query and download the standard products physically or virtually. ARIA plot is used to generate some basic qualitative plots of metrics such as perpendicular baselines or average coherence history. ARIA extract is used to extract specific layers, and ARIA TS setup itself is used to extract and prepare all required layers for time series analysis through MintPy. So it's essentially a beefed up version of ARIA extract. And just to put this into context, I'm going to stress this a few more times here, but all you need for to prepare a stack of interferograms, of ARIA interferograms for time series analysis is ARIA download and ARIA TS setup. ARIA extract does not prepare your products for time series analysis. It's meant for sort of a one-off case if you want to extract 1 or 2, let's say, co-seismic pairs, some layers for them for modeling efforts or what have you. So time series analysis to prepare for MintPy, just ARIA download, ARIA TS setup should be good. And I'm going to go over how you leverage those towards the end after first setting into context ARIA extract. But actually, just to round out some of these supplemental tools, we have a couple more. There's ARIA AOI Assist, which is used to create shapefiles for new study areas in a way that is compatible for direct deployment through ARIA and also Hype-3 pipelines. And then you have ARIA misclosure, which is used to calculate phase misclosure to assess the quality of an interferometric time series stack. The notebook outlines a nice and basic description behind what phase misclosure is as well. As far as what we're doing today, we're going to be going over ARIA extract and then ARIA TS setup. ARIA TS setup having basically the same options as ARIA extract. The only difference is how it prepares your stack for time series analysis in terms of VRT files and all that. So you're welcome to try out the other notebooks or so on your own time, but it's not required for this particular course. But before I jump into the notebook itself, are there any questions or concerns. All right, so let's move right along ahead. So we're going to start out with this ARIA extract notebook, which is perhaps the most comprehensive crash course of all in terms of ARIA tools world for the level of details with all the various options. And so to navigate to this, all you got to do is go into GeoSync, UNAFCO 2022, and it's kind of cut off here, but it's 3.3 interferogram stacks with ARIA tools. You open up ARIA extract from here, and then ARIA TS setup as well. So go ahead and open up both, but if you're gonna run them, you have to make sure to select the appropriate kernel, the UNAFCO kernel. It's very important you do. If you don't do that, your program will crash. And just heads up too, the particular version I have here, ARIA extract, you can think of it as sort of the instructor's version, meaning I already ran through it ahead of time. And other than that, it's pretty much identical. Only one that's a bit different is ARIA TS setup, is that I provided a subset of the data, I think spanning 2019 free to download on your own end, play around with, because it takes a bit longer to process the whole full archive. And by bit longer, I mean 3 hours. And I still think that that's still quite powerful to process a whole archive from 2014 up to present day, as opposed to starting from scratch with the SLC stage and topo steps and interferogram formation. So these are very nice, convenient tools, but I'm still providing very quick, efficient means for you to navigate this, at least to begin with. So yeah, in terms of ARIA extract, again, just as a quick synopsis, this function allows users to extract layers they want and modify them as needed. So there may be a scenario where you just want to extract the amplitude and nothing else, the amplitude and phase and nothing else, some combination thereof. Maybe you want to apply a water mask or not, or maybe you don't want to extract anything. You just want access to the product cut lines. You could do all of that and more. So with that, let's get started. We'll be taking a look at the product spanning the start of the 2018 Hawaii drifting event. So there's going to be this first prep stage. So I just turned the staging data to true here. We're only downloading 1 interferogram, so you can change it to false. It should be fine. But I recommend you at least keep this true for the ARIA TS setup notebook, because downloading and querying takes a lot longer than just using the stage data stored on AWS directly, downloading it, in a sense, skipping the ARIA download step and proceeding with the ARIA extract, ARIA TS setup that way. But regardless, you have to, of course, run everything in succession. Otherwise, your program processing will crash, because it's not just the data you're staging here. You're also loading some modules you're going to need, and you're also setting up your working directory, which is also going to be called in various commands thereafter from here. So load this, and then the next couple checks are going to be for your credentials. So in this next cell, it's doing this netrc check, where you have to enter your Earth data credentials. And you need this in order to successfully run ARIA download. And I know all of you have already done this, but in the likely event you haven't, take this opportunity to create your Earth data account via the listed link. And in a sense, it's sort of dummy proof in that if you go into session, the program checks if you have this hidden file accessible. If it doesn't exist, you're not going to be able to continue until unless you provide your credentials. Same idea here with Topo API. The only difference is that this is where you provide your open Topo API key as prompted, and you're going to need this to download the DEMs. And if you don't have an account for this, just follow the aforementioned link at the top here. So this is all prep steps. And then the final sort of prep part is to just run this plot layer function, so we could visualize the layers through this notebook. Okay, so now we're to the ARIA download stage. So this is, if you've already in the first prep part run with the stage data, it's not going to duplicate your efforts. You're going to avoid running ARIA download. But since I'm not going to take the time to go over the ARIA download notebook itself, you could look at that in your own time. I'll take this opportunity to give them a better description in terms of what is intended with ARIA downloads and how you use it. So there are sort of, I would say, two crucial rules to running ARIA download. First, you'd want to pass the T flag, and that's where you specify your track or path number. You have to specify a valid path number here. And then two, you need to specify the spatial footprint using the B flag. Now, you could provide this as a list of 4 numbers corresponding to a south, northwest, east bounding box, so familiar to ICE, or as I put shapefile. So I put emphasis on that because I clearly didn't follow my own advice here. I did not put an argument for bounding box, but why is that so important anyway? Why do we care? Well, this is why. For this particular case, track 124, you have scenes in Alaska. So you're going to have a hard time stitching that, or should I say that the program itself will capture this case if you have an interferogram spanning this distance, and it will kick it out. All pairs have to be spatially temporally consistent and stitchable if there are multiple frames. I'm going to get more into the details of what I mean by stitching shortly. So that said, how did I get lucky? So well, my saving grace here was that I specified with this IFG flag a pair which happened to be exclusive to Hawaii. So that's how I got away with it in this particular case. And I have these 2 products downloaded corresponding to 2 frames for 1 scene. I'm going to use scene and pair interchangeably. I'm referring to the same thing, a whole pair, be it a single frame or multiple frames corresponding to a given interferogram. Again, if you want more details on ARIA downloads, feel free to ask us questions or refer to the notebook on the ARIA tools doc GitHub page. Okay, so now let's finally get started with the namesake of the notebook itself, ARIA extract program. So don't be too intimidated by these wall of options you're going to encounter when running the help for ARIA extract. Rather, see it as sort of a welcome news, in that the suite of options translate to a good amount of flexibility and freedom to manage and manipulate your products all in-house via ARIA tools. So we're going to go over the major options in more detail through the notebook with some accompanying visuals, but please feel free to refer to the help for a more comprehensive the description of what they're intended to represent. So I'm going to start with the first 4 basic options. So the first most fundamental option is the input option, the file option. So you have the F flag here. So you could specify a relative path to a specific file, multiple files with a comma delimited list, or using a wildcard. And just to sort of back up for a second, ARIA downloads downloads everything into a product subdirectory folder. So that's why you see all these relative paths to product and whatever a given standard product is named, or with a wildcard. And it's important that when you use a wildcard, that means that you intend to extract and manage all the downloaded products. That said, you have to not omit the extension .netc at the end, because if you don't do that, then it may confuse the log files within that subdirectory as a standard product and crash. Or there's also another subdirectory within here called this duplicated product subdirectory, and that's where you have segregated out this duplicated older legacy versions of ARIA products, and it may navigate there and try to open products you don't intend to. Okay, so that said, this is pretty self-explanatory with layers. You could specify a specific layer or set of layers as a comma delimited list, or if you want to extract everything, you specify all, and then all the available layers are going to be extracted. And as far as a list, comprehensive list of all available layers, you can look at the help menu itself. Or if you don't specify anything for the layers, the program won't crash. It'll run through completion. What it'll do is it'll extract a series of product cut lines corresponding to the stitched product frames. I'm going to come back to that, I think, in step 5. And just to round out these couple of more basic options, you have the DM download and mass download options. I'm going to revisit this as well shortly, but suffice to say, if you want to You have one of two choices here. Either you could specify a path to a valid DM or mask respectively with the D and M flags, or if you want to download from scratch, you could pass download as an argument for both. But with that, I'm going to jump into this suite of cropping and spatial subsetting options. So at first glance and read through, they may sound a bit complicated and involved, but they're very simple and incredibly useful tools that our ARIA tools depends on. But before I do that, I think it's a better time than any to really kind of set into context what I mean by stitching. So for a given day, what I refer to again as an acquisition time, there may be multiple spatially continuous product frames that would need to be stitched so as to have a complete full scene. So when stitching products of each frame along track, some of the layers like amplitude and coherence involve a relatively straightforward trivial blending, which is executed by relatively minimal GDAL commands internally in ARIA tools. However, stitching of unwrapped phase fields is much more involved and complicated to perform, especially outside of ARIA tools, as it involves estimating and minimizing discontinuity across frames that is some multiple of 2 pi. So, that's just to put into context that we're accessing the extents of full scenes, these sort of cut lines for each frame that may include multiple frames for a given scene when cropping and subsetting this data through ARIA tools. So let me kind of go back here to where I was, this cropping and subsetting section. Okay, so by default, if a user specifies nothing and does not input a spatial extent with the B option, the bounding box option, the program simply defines a common cut line, which is based off of the common intersection of all scenes. And this is what you see in this magenta line here to the left. And this is a very simplified cartoon version to depict the spatial extents of these scenes, just roughly 2D and north-south. So this is sort of the common intersection of these 3 scenes. And alternatively, users could instead specify this crop to union option. Just put crop to union in the command line and instead have ARIA tools compute the common union of all interferograms and clip all scenes to these bounds. So you have this yellow line here in the right figure. So in this case, no data is going to be cropped and removed from any scene, regardless of how long or short it is. So that means the relatively shorter scenes are going to be modified to have a great deal of empty space because they just don't span great distances. Now, this option is not recommended if you wish to proceed with time series analysis, because clearly you cannot ensure complete coverage in time for all pixels. Okay, so now for this bounding box option I kept on talking about. So it's probably one of the more familiar ones from an ICE perspective, in that, like with ICE, you could specify the extent as a rectangular bounding box, so south, north, west, east, and lat, long coordinates respectively. Yes, so alternatively, and what generally myself and many of my other colleagues do, is to create a predefined custom shapefile that you could have whatever shape you want or need. In other words, it doesn't even have to be a basic box. So you could create this as a simple shapefile or GeoJSON on your own and pass it as an argument for B instead. Okay, and then finally, to round out this spatial subsetting options, we have the crucial and minimum overlap options. So we had this reoccurring, very annoying issue for larger study areas where, for instance, we're processing products across continental scales where there may be upwards of 10 frames per acquisition, and there are some outlier short acquisitions with a few frames which may skew the common track intersection of all products by default of how they're cropped to in a way that you may not necessarily intend to. So here's the common track intersection. See, it does not align with the common product bounding box. So you may end up getting clipped to an extent you don't intend for. So that's where this option comes into the play. If you think of it in terms of a bouncer for scenes, the way it works is that you enforce a specified area overlap in square kilometers with respect to your specified input bounding box, so your argument for B. So this is clearly contingent on a user input for a bounding box, because if you don't specify a bounding box, you don't have any reference to base your area overlap criteria to. So One easy way to define the bounding box in this scenario is to either draw a cut line around the extent of a scene you deem representative, either manually on your own through QGIS or Google Earth, or even more easily by running ARIA extract in initial time with no argument and copying over the extracted product bounding box for a particular scene you may deem representative. So let's say this particular scene here. And I'm going to show you how to access that in one of the examples. But with that said, going forward with production efforts to Hype 3, we have developed a procedure to ensure all products slated for production cover an entire given area of interest and avoid processing cases that don't. So that's to say this is a problem that affects legacy efforts in study areas and should not be an ongoing issue for current production efforts. Okay, so a couple more options here. We have the work directory option, which is a relatively straightforward way for you to specify a path to a directory within which you wish to deposit all outputs for ARIA tools. This is highly recommended as the default approach deposits a series of subdirectories inside the working directory that you launched the script from. And you have a unique subdirectory for each layer you wish to extract. So you could have multiple subdirectories just messing up your current working directory. And then if you want to work with alternate tracks, you're going to mix up your work and you're going to run into some issues. So you'd want to always use this work directory option to have a clean way to organize all your outputs into separate discrete directories. And that's should be straightforward. Let me know if any questions or concerns about that. And then finally, rounding out our basic key options is the output format of your extracted raster or rasters. By default, if manipulation is needed, so meaning like you have to do some cropping or some masking, then an NV format file is produced. And if not, if it's a simple case, one of the simple layers where there's not much involved stitching, like complex stitching, I should say, like the amplitude or coherence layer, then only a virtual V or T pointer file is generated to conserve space. But you may still choose whatever other GDAL supported format you want and extract those products anyway, supersede that default behavior. And you could use any GDAL supported format like GeoTIFF or even ISCE. Okay, so on to the main methods for ARIA extract. So I've kind of touched upon each of these a bit earlier. I'm going to skip over some details and go over the highlights or some of the parts I haven't really talked about up until now. So I talked about this need of the way you have this extraction with that need for manipulations. So it's more straightforward for amplitude and coherence layers, which are stitched by averaging the overlap areas just fine. But the unwrapped phase fields are stitched together through more complex means by minimizing the 2π jump between frame boundaries. But I need to go now into some more detail about how the metadata layers are extracted. So the method of extracting geometry layers, such as perpendicular baselines, incidence angles, and azimuth angles, is a bit more complex compared to even the unwrapped phase field layer. That's because the geometry layers have been downsampled to a roughly 10-kilometer posting at discrete height levels of 3 kilometers. So they are distributed as, you could think of as coarse cubes. This is possible as these layers are smoothly varying spatially anyway, and downsampling will help to significantly reduce file sizes and thus help with the portability and storage costs. It keeps each standard product to roughly around 60 megabytes. So we'll demonstrate how these layers can easily and reliably be interpolated through ARIA tools. The resampling and conversions for a coarse cube to a standard 2D raster of the same resolution as the extracted unwrapped phase field involves interpolation in intersection with the heights in a full resolution DM file, which is sort of denoted by this little cartoon volcano. Think of that as the DM here. Okay, so that was a lot of setup, a lot of context here. So before we jump into the questions, I'll take a little breath, a little water break. So let me know if you have any questions or concerns in the meantime. Okay, so now on to example 1. We see that if we run ARIA extract with no other arguments other than the input products themselves with the F flag again, the program simply computes and creates shapefiles recording the spatial extent of each interferogram and deposits them in the product bounding box subdirectory. So here in this case, we have two frames that overlap and correspond to the same time. So they're stitched together into a single IFG cut line. It's the pair name.geojson. Additionally, also generated are two general product bounding boxes corresponding to the common scene union. You have the product bounding box crop to union, and then also another one corresponding to the common scene intersection, product bounding box GeoJSON. But because we only have one scene here, all these cut lines are identical because you're not having a common intersection between multiple scenes. It's just one scene. So that's to say, you do have multiple products. These will be all different. And if you instead wish to clip all your products to the bounds delineated by the common union, you'd have to pass the flag crop to union. Otherwise, it's this product bounding box, the common track, intersection, which is what everything is going to be cropped to. Okay. So in our second example, we're going to start extracting product layers and experimenting more with product cut lines. So I'm going to be intentionally taking some baby steps and extract layers and iterative steps, but this is not necessary. You don't have to download an app. You don't have to extract amplitude and then coherence and then incidence angles separately. You can do it all in one shot. I'm just trying to demonstrate the different layers here. But anyway, here we specify the download of the amplitude file by just saying amplitude itself here as an argument to L. And what we get is an output and aptly named amplitude subdirectory of this underscore uncropped version, which is before the cut line was applied, and then the final version pair.vrt to which the cut line was applied. And again, since we only have one scene, these are identical. And they both point to the original product itself. Note that the final product, this pair.vrt option, is what is pushed through for time series analysis via RATS setup and made visible. And note too that these are both virtual files. There's no physical files extracted. And that's again the default behavior for these basic layers like amplitude and coherence. And if you don't want this, if you want to supersede this behavior, if you want physical rasters extracted, then you're going to have to specify as an argument to output format one of the GDAL supported formats, like even ICE or a GeoTIFF or so. And finally here, we could visualize the amplitude layer itself. So recall again the significance of the amplitude layer, which serves as a record of the backscatter, which is a proxy for the complexity of the surface or strength of the signal. So rougher surfaces with strong returns, such as exposed stable bedrock, may appear bright, while smoother flat surfaces are very complex surfaces, such as tall vegetation obscure signal, such that there's low return. Okay, so in the next part here, we're going to be, in addition to extracting the coherence and sort of new layer, we're going to manually specify a tighter bounding box with the bounding box arguments, which B box again is synonymous to the B flag. And you could see this in the help guide as well. There's sort of multiple synonyms for the same option. In this case, B equals B box and file equals F or so. You can see a comprehensive list with the help guide. Let me know if you want me to clarify that. But regardless, we specified a box here. It's no surprise we end up getting a product bounding box, which looks like a box. And when we go ahead and display the coherence, we see it's a much tighter bound that is set to the Big Island of Hawaii itself. And the coherence file itself is going to be generated into a separate coherence subdirectory, again with uncropped versus the final cropped version. Yeah, so what is the significance of the coherence file? So coherence is a quality measure of interferometric correlation. It ranges from 0, where there's no useful information in the interferogram, to 1, where in theory there's no noise and it's a perfect pixel or so in the interferogram. The coherence layer itself here has been multi-looked to an approximate resolution of 450 meters and is thus intended as a very crude measure of correlation. You could get an idea of how coarse this data is by just looking at this little boxy artifact resulting from the large averaging windows that were applied. Okay, now time to extract the geometry file, in particular the incidence angle file. You specify that with the L flag again. And I'm gonna be showcasing a bit more flexibility with the leveraging shapefiles. In particular, we're gonna use this sort of pre-prepped file where we have outline of the big island itself. And everything outside of this is masked out. So you could think of this as a literal cookie cutter. So just so happens that all the oceans obviously are going to be masked out. So now given this modification and the fact that geometry files need to be interpolated, you need a DM at your disposal. A physical raster must be generated. So we can't rely on a virtual VRT pointer itself. See, there's no single VRT pointer. We have an actual raster extracted because this is a non-trivial means of where we can't just point to within the standard product itself. And we're going to need the DM to perform this interpolation. So you have to manually either specify a path to a valid DM or specify the download of a DM from scratch with the D flag. If you don't do either, it's going to crash if you're trying to extract any geometry layer. So that part's important. And just to sort of demonstrate the reliability of this interpolation method, you can see how smoothly varying and clean the final incidence angle field is. And then we have an example where we're downloading a mask. So we're not always going to be lucky to have a nice convenient shapefile at our disposal to clip oceans and other water bodies out of our products. No, we waste so much time manually kind of creating our own impromptu cut lines that way. Instead, with ARIA tools, we may actually download a mask from the GSHHG database, which for those of you that are familiar, is the same source used by the GMT software for delineating water bodies. If you don't want to use that source, you may alternatively use the NLCD mask, which is managed by USGS, by simply specifying NLCD as an argument for a mask instead, or you may specify a path to your own separate mask file as long as it's valid as an argument. And the result is pretty straightforward. This is a binary file. You're going to get 1, which is denoting land, and then 0, which is denoting water. And clearly the oceans are captured well, and the mask is applied as intended to the layer we request to be extracted, which turns out to be the unwrapped phase field itself. So this is our first look at the unwrapped phase field, because that's what I had requested to be extracted in L this time. Sorry, I have the flights. I'm just checking these updates. Okay, sorry. So I'll skip over some background behind downloading a DM. So since I've already kind of covered most of the bases, but suffice to say, we download SRTM DM sampled at 90-meter resolution. Hence, their default output name is going to be SRTM 3 arcsecond, and it's going to be deposited inside of a separate DM subdirectory, like is the case for all these other layers. And with the mask itself, it's inside of a mask subdirectory. So it looks as we'd expect for the Big Island. You have high topography for this large volcanoes, Mauna Kea and Mauna Loa, and then near sea level values, well, near the sea itself. And yeah, that rounds out the examples. So I'm just going to go over a couple very quick applications of relevance for more involved modeling and analysis efforts, starting out with the derivation of the east-north up conversion factors you're going to need for modeling. The unwrapped phase fields we've seen demonstrate in a satellite's deformation in a satellite's line of sight. So if we want to translate modeling outputs from the standard east-north up directions into the line of sight, we can directly compare with INSAR observations. Then we'll need to leverage some simple trig involving geometry files to derive these corresponding scaling factors. And anyways, we're going to need the incidence angle file, which is the angle of the radar with respect to a vertical. And we're going to need the azimuth angle, which is the counterclockwise angle between east and the look direction from the ground target to the center. And there's this little simple procedure via this Python blurb that we use to derive these conversion factors. And they're going to be outputted into this physical cube that we're going to display the separate layers here, the east, north, up layers. So note the relative levels of sensitivity our INSAR measurements have to certain directions. These values have, for the vertical scaling factors, are high. For instance, you can see in the scale here, meaning INSAR is especially sensitive to the vertical direction. This is because the angle of observation with respect to the ground is pretty steep. On the other hand, INSAR is relatively insensitive to the northern direction given the low values for the scaling factor, since it's more in line with the flight path of the satellite and thus not well resolved with line of sight. And on the contrary, the sensitivity to the east direction is high as the line of sight is well aligned again with the satellite's roughly north-south flight path, given it's more in line to the east-west direction. Okay. So finally, we have this one little last simple example where it's a procedure to convert the unwrapped interferogram, which is distributed in radian units, to a more digestible unit of centimeters. We do this by taking note that the conversion involves multiplying the raw phase with a factor that consists of the sensor wavelength, which for Sentinel is roughly around 5 centimeters. Divided by 4 pi, as you can see in the expression here. And we could execute this through a simple GDAL expression. You know, this is going to be the argument that you have for calc. Very straightforward procedure. You apply input being the unwrapped phase, you have connected components, default format NV, and we end up getting the deformation in centimeters. Keep in mind that the phase convention of the field is positive for uplift, so we see a discrete focus zone of subsidence here, this blue part, which turns out corresponds to deformation resulting from magma withdrawal away from the Kilauea rift zone and to the east. Okay, so that's all there is for the ARIA extract notebook, and it shouldn't take more than 10 minutes for the ARIA TS setup, as you see shortly. But is there any questions or concerns for this before I close out and move on?
There was a question, quite a lengthy one, some way back in the chat, about bounding boxes and MOs. I'll try reading it. If you had an irregular shaped bounding box that generated a large number of interferograms, would you need to set a higher MO to not have so many of them rejected?
So the limit obviously to the MO then would be the area of the bounding box you specified. So if once you hit that peak and you end up having seams that you still think are too short, that means you need to adjust your bounding box itself. You need to manually make that bigger, or look at one of the output product bounding boxes in the product extend subdirectories here. So like here, this is this pair. Let's say that there was another pair in 2019 that was representative of what you want. What we do generally is we just take that, and I mean my colleagues meaning, we take that, we have that as sort of our template working bounding box, and then we use that as a guide to drive the MO. It's a bit complicated there, but does that clarify that?
I hope. So you're saying that you should just measure the area of that with your bounding box and have that as your MO? Would that?
Pretty much, yeah. That's one way to go about it. But that said, I think maybe in retrospect, maybe something I could have on my checklist as a convenient way to sort of manually go about measuring that. Maybe I could have a little option which you use the area, like the program reads it for you instead of you doing the manual legwork. So that's something I just realized now, but I could implement. So yeah, sounds good. Does that make more sense?
I believe so, yes.
Okay.
There's a couple of people having errors. It's not clear that those are your fault so much as like credential problems.
Yeah, get your credential, guys. It's important, especially to download the products. But if you're having credential issues with Earth data, for instance, just use the stage data. You're gonna need a Topo API account to download the DMs. There's no way around that, though.
Someone's having a value error with converting. What is it? Trying to cut the outline of the big island, I think. I'm not sure what the origin of that is. Might it be that you might be jumping a step somewhere?
Yeah, that's what it sounds like to me. You have to run everything in succession. If you don't, then the processing will break. So that's an important part there.
If you've not extracted a shape file, then yeah, you can't apply it later on. That might be the problem.
Yeah, that makes sense. But if you're using the predefined cut line, then that shouldn't be relevant. That's what's funny. So I would do what I would do if I were you, I'd do a PWD. I would open up a new cell here like this and make sure I'm in the right working directory. Do an ls for that particular file, that command line, do ls, whatever that relative path is. And if that doesn't work, you're not in the right directory. And that again is resolved if you start from the prep at the top. You have to run and it enters the appropriate working directory you need, which is going to be separate for ARIA extract and ARIA TS setup.
Great, thank you. Has anyone else got any questions on this notebook for Sim before he moves on?
Okay.
You're in the clear.
Great. So this part shouldn't be more than 10 minutes because, like I said, ARIA TS extract is basically a beefed up version of ARIA extract, and it's essentially a wrapper script. So it shares exactly the same options and much of the same functionality. The only difference is that it makes sure all the prerequisite requirements for time series analysis through Mint PY are met. And these requirements include the extraction, of course, of the unwrapped phase field itself, and also the coherence imaging geometry files as well, such as azimuth, incidence angle, and loc angle. And since we're going to extract the azimuth angles, then you need to obviously specify either path to a valid DM or the download of a DM from scratch. And that again said, and I do want to sound like a broken record here because it's important to state, for time series analysis, to prep for time series analysis, you only need to do two things: ARIA download, ARIA TS setup. That's it. You don't have to go through the other tools for that prep. So with that said here, we're not going to be looking at Hawaii in this case. We're going to be looking at a track over the San Francisco Bay Area. And just like ARIA extract, we're going to run through the, it's important to run through the first initial prep sections, check the UNAFCO kernel up on the top right. But yeah, go through these checks here. Don't change the stage data here, keep it to true, because it'll take a little bit longer to download the data from scratch as opposed to just using the stage data. And I'm going to get a big wall of text here because I've downloaded everything over this Bay Area from 2014. So there's that. It's going to check for the NetRC in the Topo API, so on and so forth. Okay, and then you have the download here, products, yeah, it's all deposited here. I'm gonna have to use this cursor. Okay, this is you have the help here, which is using the same options as ARIA extract. So I'm gonna skip over that because that's redundant. And I'm going to go to the application. Okay, here's the application, the basic bare bones method for prepping the stack for time series analysis. Note, you don't have to specify the extraction of any layers because the minimum required layers are extracted. But if you want to extract the non-default layers, specifically the amplitude, then you'd need to specify that as an argument for layers. And then it's going to append that to the list of layers that you need to extract. And we're going to have to download of a DM. And since this is the San Francisco Bay Area, it's very crucial to have a water mask. So I'm going to skip over some basic displays here. Yeah, this is something maybe we have to clean up here. It's all these checks done and a big wall of text. Okay, so we already saw the water mask. Previous exercise. Here's interferogram. I'm going to come back to that later. DM, similar idea. Yeah, so I think I'm going to, the final sort of important aspect of ARIA-TS setup, which is distinct from ARIA-Extract, is this generation of a stack directory containing 3 distinct VRT files. The VRTs are named coherent stack, connected component stack, and unwrapped stack respectively, and they contain pointers to each of the coherence rasters, connected component rasters, and unwrapped phase fields as so. You know, if you do a GDAL info, you're going to see roughly how they're called in sequential order. Let's skip down from this text here. You could do a GDAL info to get relative paths. You can access the metadata itself, so the average perpendicular baseline for each of the bands or so. This is all, the point of all of this is to make it compatible and seamless for time series analysis through MintPy. And the MintPy program expects these virtual pointers to access the relative metadata and pointers to the VRT files. So you could sort of think of these VRTs as a baton in the last leg of a race, or should I say in this case, marathon. And finally, you have the display of one of the unwrapped phase fields. So I directly plot the layers from the unwrapped stack to the very first interferogram in that stack. So it's a pair around 2014 or so. So note that this isn't a co-seismic interferogram. There's no clear deformation. It has probably a very short temporal baseline, so it's difficult to deduce any deformation here. Plus, there's a good deal of noise. So that's where time series analysis comes into play, as it can help to better articulate a longer term record of deformation and average out this transient noise. And that's all I got today. So I could open up the floor to questions, concerns, or what have you. Let me see the.
It's a nice picture of a tropospheric noise.
Yeah. I remember when I was a student under you, Eric Fielding, you asked if I processed a stack of programs over Oklahoma as sort of good case studies of where you don't see any deformation, just tropospheric noise. So.
Is that an unwrapping error offshore of
Yeah,
the Golden Gate?
this does look like an unwrapping error, and this is something which maybe you probably want to mask out, or for MintPy, I'm not sure how, this is maybe something that's addressed with the unwrapped phase correction option or so, but that's not something that's handled on the ARIA tools end. It's just prepping it for time series analysis, not doing this post-processing steps within that pipeline. Is someone asking something? I can't hear.
I don't think so.
Oh, I thought I heard someone. Okay.
Well then, if there are
Nice
no
job.
questions, that was awesome. How to prep like thousands of interferograms for automated analysis in MintPy. Will this output be used in the MintPy time series analysis? The answer is yes.
Yeah, that's correct.
What is the question now?
That was the question.
So will this output be used in MintPy time series analysis?
Yes, it will. And a separate step of that I think Jenssen's going to go over. But as far as ARIA tools is concerned, that part is done. We've prepped it for time series analysis. We could proceed directly with MintPy from here.
You need to make sure that, yeah, you've made those 3 stack files.
Yeah, which is handled with ARIA-TS setup. ARIA-Extract does not generate those VRT pointers. So that's why if you want to go through MintPy, you have to run ARIA-TS setup. Only use ARIA-Extract if maybe you want to look at one interferogram pair for like a closed seismic case or so where you don't care about time series analysis. You just want to do some modeling. That's the only time you really should use ARIA-Extract itself in lieu of ARIA-TS setup.
So make sure you've run this before Friday. So we can only download unwrapped Sentinel-1 interferograms. Well, that is what these are, yes. If you want to download SLCs or something else, you can get those from ASF.
Yeah.
Not other sensors, and the answer is no.
Not yet.
Something like this will be available for NISAR when NISAR is launched. Paul will tell us about that, hopefully. later.
Yeah, there will be some custom processing capabilities coming for ALOS, sort of old ALOS data, more archived ALOS 1 data sets, and then for NISAR also, but currently it's mostly Sentinel-1.
As I mentioned in the chat, this ARIA HDF5 format of the GunW files is very similar to what we're going to be using for NISAR. So this is like a prototype for the NISAR GunW GNW products. It's going to have the same kind of structure. It will be slightly different, of course, because it'll be NISAR data instead of Sentinel-1. It has to have some slightly different information, but we'll have something very similar to ARIA tools that'll be used for NISAR data.
And the whole funding for the development of this workflow and everything was with that in mind.
Yes,
Question about
the getting ready for NISAR.
I don't know if I heard a question again. It was kind of cut off.
Nobody systematically processed the UAVSAR data. I think there were some proposed projects to do that. I don't know if any of those projects have been funded. The amount of UAVSAR data is huge, so it's actually almost as big a project as the ARIA processing.
There are interferogram stacks, right, available for UAVSAR. They're just not.
Yes, there's UAVSAR SLC stacks. These are they're co-registered SLCs that are easy to make into interferograms. In fact, we use the same strip map stack processor that can be used to process other strip map data, to process UAVSAR data. Because the data is already co-registered, we can skip a lot of the steps and just form interferograms, do some filtering and phase unwrapping, and then strip map stack writes out the data in a format that's easy to load directly into MidPy, similar to what we do with ARIA tools.
And so if you think of sort of this part of ARIA tools to be a preparation for time series processing, there are really only a few places where this is relevant for UAVSAR. As an airborne data set, you don't have, dense time series of UAVSAR data in random places. You have them in some places. There are good stacks in California where you can use and work with UAVSAR data. But in most other places, the sampling in time with UAVSAR is either non-existent or sparse.
San Francisco area happens to be one of the places where we've been acquiring UAVSAR data since 2009 under a number of projects that I've been running. So there's actually a lot of UAVSAR data in exactly the same area that Sim was showing for San Francisco, but not everywhere.
And also,
mostly in California.
There's also good coverage over Central Valley too, right, Eric? Or continuous coverage?
Yeah, there's a dense coverage over the Sacramento River Delta.
Yeah.
There was a question about whether it's possible to use this to select interferograms that don't have too many errors. I guess.
Well, no, that's not. It is sort of down selection to ARIA tools is not supported outside of spatial down selection itself. That's something that you could do in ARIA tools itself. I mean, ARIA tools in MintPy itself, though, you could specify the indices of particular products to extract, I should say exclude. But with that said, there actually is a check in ARIA plot where it omits files which have a average coherence of less than a specified threshold. So that's something that could be easily extended to maybe kick out pairs as well, but that's just an idea I have. It's not something supported in terms of the quality of a pair itself.
Yeah, I imagine you could probably find a way of extracting, or there's a way you could look at the variance of an interferogram unwrapped phase. If it's not an earthquake, say, oh, look, this is really noisy, but that's not written yet.
Yeah, and so when we talk about MinPy on Friday, you'll see that there are a number of knobs that you can twist in MinPy to remove certain interferograms that are not that great. There are coherence checks, there is an unwrapping error correction, DM error correction that you can apply, and I think Yunjun is going to walk us through those different options on Friday.
All great questions. I think we are probably slowly running out of steam. Sim's got a flight to catch. What about the pixels which have with poor coherence and high errors in each interferogram? Again, that's something you can identify potentially in MinPy itself.
Right. Yes. Yeah, so Yunjun is going to show you a few tricks of, helping you identify bad data and clean data as you go through the time series processing.
So I think Sim, you are off the hook.
Sounds good. And that said, Gareth mentioned I'm leaving town. So my TAs, fellow developers, Emre and Brett, they'll be back for the office hours. They'll be in communication by Slack. I'll have my phone with me in Slack as well, so I'll be able to address any quick questions. But Emre and Brett will probably be able to provide more direct feedback, and they'll be around this evening, both of them.
Yeah, you shouldn't have your phone switched on for this course. Go enjoy yourself.
Yeah, we have we do have office hours at 5 p.m. Pacific time today.
And maybe there's one more thing to talk about, which is what we would like you to do for homework. Very briefly share my screen. I got the right window. Yeah. Okay. So for today, there's two things. One is to use the notebooks from module 3.1, the very first thing this morning, to model a different earthquake. Right now, I am trying to find someone on the ASF team who will stage an earthquake's worth of data for me. I've not got any response, but I'm saying this now so that France can hear me. I have an interferogram uploaded to OSL, which I would like to put in a bucket for AWS so that you can download a pre-processed interferogram, or of course, you can always process your own if you're feeling particularly enthusiastic. I can give more details in Slack about the AWS bucket as and when everything gets done. And the other thing is to complete the module that we've just been watching, specifically downloading those stage data and making sure that you complete the interferogram stack aspects of ARIA TS setup. And print out.
Gareth, did you contact them on Slack?
I mean, yes.
Okay.
Or Alex is copied into the thread. I don't know. He didn't respond. He might be busy though if the archive went down today.
I just contacted him. I'm just going to find the. Okay, I see it.
You got it?
Yep.
Cool. Thank you. And with that, I think we are done for the day. Thanks everyone for coming. Thanks for sticking with us to the end. It was an information dense afternoon, and I think we will make good use of that information in the next couple of days.